Look up at the night sky. See those tiny, brilliant points of light. Each one is a star, a sun, possibly with its own family of worlds. Some of those stars are so unimaginably far away that their light has been traveling for millions of years just to reach your eyes. It's a beautiful, humbling thought, but it raises an absolutely fundamental question for astronomers. How do we actually know how far away any of it is? We can't just stretch out a cosmic tape measure. So how do we map the staggering vastness of the universe? The answer to that question is one of the most elegant and powerful tools in all of astrophysics, and it involves a special class of stars that act as celestial lighthouses, guiding us through the dark. These are the Red Clump Giants, and they are our universe's most reliable standard candles. They are the key that unlocks the scale of everything we see, allowing us to measure distances across millions of light years with remarkable precision. Without them, our cosmic address would be a mystery, and the grand story of the universe would remain frustratingly out of focus. Think about that for a moment. Our entire understanding of the cosmos, its age, its expansion, its very fate rests on our ability to accurately measure how far things are from us. It's the most basic piece of data, and yet it's the hardest to get right. For centuries, astronomers struggled with this very problem. They knew the universe was big, but they had no true sense of its scale. It was like having a map of the world with no numbers, no scale bar, just shapes on a page. You knew the general layout, but you couldn't calculate a real journey. That all changed when we learned to read the light from these specific, predictable stars. This journey into cosmic cartography is a story of human ingenuity meeting celestial consistency. It's about finding patterns in the chaos, about discovering the reliable beacons that nature herself has provided. And as we explore this concept together, you'll begin to see the night sky not just as a random scattering of lights, but as a structured, measurable expanse, a cosmos we are finally learning to navigate. So let's embark on this voyage of discovery to understand how a specific group of aging stars gives us the ruler we need to measure the universe itself. To grasp how we measure these cosmic distances, we first need to understand a beautifully simple but powerful idea, one that astronomers call a standard candle. Think about a standard candle not as a star but as a concept. Imagine you're standing on a long, dark road at night. You see a light in the distance. Is it a dim light close to you or a fantastically bright light very far away? Just by looking, you can't really tell. But what if you knew with absolute certainty that the light was a standard 100-watt bulb? Suddenly, you have the key. You know its true intrinsic brightness. So by measuring how faint it appears to your eye, you can calculate exactly how far away it must be. The dimmer it looks, the farther away it is. This is the fundamental principle behind a standard candle in astronomy. It's any celestial object whose true, inherent luminosity we know. Once we have that one crucial piece of information, its actual wattage, so to speak, the vast, empty space between us, and it becomes measurable, we simply compare its known true brightness to its apparent brightness as seen from Earth. The difference between the two, that dimming, is directly due to distance, and the math to calculate it is remarkably straightforward. This method is so vital because it's a direct measurement. Unlike other, more complex geometric techniques that have severe distance limits, standard candles can, in theory, be used to gauge distances clear across the observable universe. But of course, the entire system rests on one critical assumption, that we have correctly identified the object's true brightness. An error there, and our entire cosmic distance ladder, the step-by-step method we use to measure the universe, would collapse. So the hunt in astronomy has always been for reliable, identifiable objects that nature produces with a consistent, predictable luminosity. We need celestial lighthouses whose beacon we can trust, whose light output is so uniform and well understood that it can serve as a universal milepost. This brings us to one of the most elegant frameworks in all of science, the cosmic distance ladder. Think of it less as a single tool and more as a chain of interconnected methods, where each rung supports the one above it, allowing us to climb from our own cosmic backyard out to the very edge of the observable universe. The beauty of this ladder is that no single technique can do the job alone. Each has its own range of reliability, its own sweet spot. The base of the ladder, the first and most fundamental rung, is a method called stellar parallax. It's a concept you can experience right now. Just hold your thumb up at arm's length and close one eye, then switch eyes. See how your thumb seems to shift position against the background. Astronomers do the exact same thing with nearby stars, but instead of using their two eyes, they use the Earth's orbit around the Sun. They observe a star's position against more distant stars, then wait 6 months and observe it again from the other side of our orbit. The tiny shift in the star's apparent position, a fraction of a degree, allows for a direct geometric calculation of its distance. It's the most straightforward ruler we have. But here's the catch. This method only works for stars that are relatively close, within a few thousand light years. Beyond that, the parallax shift becomes immeasurably small, like trying to see a dime shift position from dozens of miles away. So we need a new method, a new rung on the ladder to reach further. This is where standard candles come in, serving as the indispensable middle rung. We use the reliable, close-by stars measured by parallax to calibrate the true brightness of certain standard candles. Once we know with confidence how bright a particular type of star actually is, we can then identify that same type of star in a more distant cluster. When we find it, we measure how faint it appears. That dimming gives us its distance directly. This is the brilliant hand-off that powers the entire ladder. We use a direct measurement to calibrate an indirect one, and then we use that calibrated indirect measurement to leapfrog out into the cosmos, but the ladder doesn't stop there. With these mid-range standard candles, we can measure distances to nearby galaxies, and within those galaxies, we can find even brighter, more powerful cosmic beacons, like a special class of exploding star known as a Type 1a supernova. These supernovae are so brilliant they can outshine an entire galaxy, making them visible across billions of light years. By studying these supernovae in galaxies whose distances we already know from our mid-range candles, we can calibrate their true brightness, adding yet another, even higher rung to our ladder. This step-by-step process, each rung securely fastened to the one below it, is what allows us to confidently measure the mind-boggling distances to galaxies so far away that their light is a fossil from a time before the Earth even existed. The cosmic distance ladder is therefore a testament to scientific ingenuity, a patchwork of methods that, when woven together, creates a single, unbroken chain of evidence stretching from our own solar system to the very dawn of time. So where do we find these reliable cosmic lighthouses, these standard candles that are both bright enough to see at immense distances and predictable enough to trust with our most fundamental measurements? The answer lies not with the brilliant, short-lived superstars of the cosmos, but with a much more common, stable, and unassuming class of aged stars known as Red Clump Giants. To truly appreciate why they are so valuable, we need to take a quick tour of stellar retirement. A star like our own Sun spends the vast majority of its life in a stable, middle-aged phase we call the main sequence, quietly fusing hydrogen into helium in its core. But eventually, that central hydrogen fuel runs out. The star's delicate balance is disrupted, and it begins a dramatic transformation. Its core contracts and heats up while its outer layers expand and cool, turning the star into a red giant. This is a turbulent, complex phase, but for a certain group of stars, a period of remarkable stability follows. After the initial red giant stage, the core becomes so hot and dense that it begins to fuse a new element, helium. For a specific range of stars, those with masses roughly similar to our Sun, this ignition of helium doesn't happen with a violent explosion, but in a sudden, peaceful flash. The star settles down and enters what is essentially its retirement home. This is the Red Clump. Imagine a star has been through its wild, expansive youth as a red giant. Now it finds a comfortable, stable equilibrium. It's burning helium into carbon and oxygen in its core at a steady, predictable rate. It's no longer expanding or contracting dramatically. It has reached a comfortable phase of life where its internal processes are beautifully consistent. This consistency is the astronomer's gold, because these stars are all doing the exact same thing, fusing helium in their cores under very similar conditions. They all have nearly the same true intrinsic brightness. Think of it like a factory producing 100-watt light bulbs. Each bulb might look a little different on the outside, but because they are all built to the same specifications and powered by the same electrical current, they all output the same amount of light. Red clump giants are nature's version of that perfectly standardized light bulb. Their position on the star family tree, the Hertzsprung-Russell diagram, perfectly illustrates this. This diagram plots a star's color against its brightness, and it reveals clear groupings where stars of similar evolutionary stages reside. The main sequence is a long, diagonal band where most stars, including our Sun, lie. But the red clump is a distinct, tight little knot of points sitting in a specific region of the diagram. They aren't scattered all over the place. They are clustered together, a clear indication that they share almost identical properties. Their brightness is so uniform that if you find one in a distant star cluster, you know its true luminosity with an uncertainty of less than 5%. This predictability makes them perfect for our cosmic distance ladder. They are bright enough to be observed in nearby galaxies, providing a crucial link between the local measurements from parallax and the vast distances we need to probe to understand the expansion of the universe itself. So what specific properties give red clump giants this coveted role as cosmic mile markers? Their excellence stems from a powerful combination of uniformity, visibility, and identifiability. First and foremost is their remarkable consistency in true brightness, because they are all undergoing the same fundamental nuclear process, the steady fusion of helium in their cores. Their energy output is incredibly predictable. It's like a vast forest of trees that have all reached the same mature height. While they might be different species, their shared stage of life means they dominate the canopy uniformly. Astronomers have measured thousands of these stars, and their intrinsic luminosity clusters tightly around a value about 50 times brighter than our own Sun. This small margin of error, often less than 5%, is what makes them so trustworthy. You can send a spacecraft to measure the distance to a nearby red clump giant using parallax, confirm its true brightness, and then with great confidence, apply that same brightness value to a red clump giant you spot in a distant galaxy. That reliability is the bedrock of their utility. Another critical advantage is their sheer abundance. You don't want a standard candle that's so rare you can barely find it. Red clump giants are common. Stars with masses similar to our Sun are extraordinarily plentiful throughout the universe, and nearly all of them will pass through the red clump phase in their old age. This means in almost any large group of stars, whether in the disk of our own Milky Way, in the dense central bulge of a galaxy, or in the sprawling clusters that orbit galaxies, you are likely to find a population of these stable, aging stars. They provide multiple, redundant data points within a single galaxy, allowing astronomers to cross-check their measurements and build a more robust and accurate distance calculation. It's the difference between trying to triangulate your position with a single landmark versus having a dozen different landmarks all visible at once. This abundance transforms them from a curious astronomical oddity into a workhorse tool for mapping the local universe. Furthermore, they strike a perfect balance in terms of brightness. They are not so faint that they get lost in the background glare of a galaxy, requiring impossibly long telescope exposures. Yet they are also not so catastrophically brilliant that they are fleeting and unpredictable, like a supernova that blazes for only a few weeks and then vanishes forever. A red clump giant will remain in its stable phase for tens of millions of years, a veritable constant in the cosmic landscape, giving astronomers all the time they need to make careful, repeated observations. This longevity and moderate brilliance make them ideal for studying the structure of our own Milky Way and for peering into nearby galaxies within our local group like Andromeda and Triangulum. They act as a bridge, illuminating the middle ground of the cosmic distance ladder with steadfast reliability. Perhaps just as important as their consistent brightness is how relatively straightforward they are to identify. An astronomer can't just look at a faint speck of light and instantly know it's a red clump giant. They need a way to pick them out of a crowded star field. Fortunately, these stars have a distinct spectral signature. By breaking a star's light down into its component colors, much like light passing through a prism, scientists can read the unique chemical fingerprints in its spectrum. The specific conditions inside a red clump giant, its temperature, surface gravity, and composition, produce a telltale pattern of spectral lines that is quite different from a younger main sequence star or a more evolved red giant. Additionally, their position on the Hertzsprung-Russell diagram is a dead giveaway. When observing a star cluster, astronomers plot the brightness and color of all its stars. The red clump giants will conspicuously clump together in a distinct, tight grouping, separated from the other evolutionary tracks. It's like being able to pick out all the people in a massive crowd who are exactly 6 feet tall. They stand out as a coherent group. This ease of identification, combined with their uniformity and abundance, creates a perfect storm of utility. They are nature's gift to cosmography, providing a legion of standardized beacons that allow us to move from simply admiring the stars to truly measuring the architecture of the cosmos they inhabit. To truly appreciate the elegant physics that makes a red clump giant such a reliable beacon, we need to peer into the final chapters of a star's life. It all begins when a star, much like our own sun, exhausts the hydrogen fuel in its core. For billions of years, this hydrogen fusion has provided the outward pressure needed to balance the immense inward pull of gravity, creating a stable equilibrium. But when the hydrogen is depleted, that balance is catastrophically upset. The core, no longer able to support itself, begins to contract under its own weight, heating up to incredible temperatures over 100 million degrees. This fierce heat ignites a shell of hydrogen fusion around the now inert helium core. The energy from this shell fusion causes the star's outer layers to expand dramatically, cooling as they do so, and the star swells into a red giant. Our own sun will undergo this transformation one day, growing so large that it will engulf the orbits of Mercury and Venus. This is a turbulent and relatively brief phase, lasting only a few 100 million years. The star is essentially in a state of upheaval, its size and brightness fluctuating as it searches for a new stable state. The turning point arrives when the collapsing core of helium becomes so incredibly hot and dense that it reaches a critical threshold. Under these extreme conditions, a new and exotic physical process begins. The helium nuclei, which are the ash from the previous hydrogen-burning era, themselves start to fuse together. This isn't a gentle process, it's initiated in what astronomers call the helium flash. For a star of solar mass, this flash is not a destructive explosion, but a sudden, violent burst of fusion that occurs throughout the core in a matter of seconds. It's a spectacular stellar event, releasing as much energy in that brief moment as our sun will over its entire 10 billion-year main sequence lifetime. Yet, remarkably, this flash is entirely contained within the core. From the outside, we wouldn't see a thing. its purpose is not to destroy the star but to rescue it. The enormous energy released from the helium flash heats the core so effectively that it stops contracting. The star, which was teetering on the brink of instability, suddenly finds a new and incredibly stable form of nuclear fusion. This is the moment the star enters the red clump. With the core now steadily fusing helium into carbon and oxygen, the star achieves a new, long-lasting equilibrium. The reason for its remarkable consistency lies in the unique nature of this helium burning process. The core at this stage is what physicists call electron degenerate. The matter is so densely packed that the electrons are stripped from their atoms and are forced into a state where they resist further compression with tremendous pressure. This degeneracy pressure, which is a quantum mechanical effect, acts as a powerful regulator. It means the core's size and temperature are almost independent of the star's initial mass. Whether a star started its life 10% more or less massive than the Sun, once its core becomes degenerate and ignites helium, the physical conditions in that core are forced into a very narrow range. Since a star's brightness is directly determined by the temperature and pressure in its fusion engine, this core uniformity translates directly into a uniform luminosity. They all settle into shining with roughly 50 times the Sun's power, becoming those perfectly standardized 100-watt bulbs in the cosmic darkness. This helium burning phase is also notably long-lasting and stable, providing the dependable longevity that astronomers rely on. A star will spend about 100 million years in the red clump, which is long enough for us to observe it in countless galaxies, yet short enough that there is always a fresh population of stars entering this phase to study. The stability comes from a beautiful feedback mechanism. If the fusion rate in the core were to briefly increase, producing a little too much energy, the core would try to expand and cool, which would in turn slow the fusion rate back down. Conversely, if fusion slowed, the core would contract and heat up, speeding fusion up again. This self-regulating, thermostatic control is what keeps these stars shining so steadily for millions of years. They are not experiencing the dramatic death throes of a supernova or the frantic instability of their earlier red giant phase. They are in a comfortable, mature period of their lives, burning their fuel in a slow and predictable manner. It is this rare combination of a standardized core process and a long, stable duration that elevates the Red Clump Giants from mere interesting stellar objects to the fundamental calibration points upon which we build our map of the local universe. Of course, Red Clump Giants are not the only lighthouses we have in our cosmic toolkit. To fully appreciate their unique role, it helps to compare them to two other famous standard candles, the pulsating Cepheid variable stars and the Titanic Type 1a supernova. Each of these tools is brilliant in its own way, but each also comes with its own set of complexities and limitations. Cepheid variables, for instance, are truly cosmic powerhouses. These are massive stars that rhythmically pulse in size and brightness over a period of days or weeks. The key to their usefulness is a beautiful relationship discovered over a century ago. The longer their pulsation period, the higher their true intrinsic brightness. This period luminosity relationship is a powerful tool, allowing astronomers to measure distances to galaxies tens of millions of light years away. However, Cepheids have a few notable drawbacks. They are relatively rare as they are only produced from massive, short-lived stars. More importantly, they are not perfectly simple. Their pulsations and their relationship with brightness can be subtly influenced by the chemical composition of the star, its metallicity. This means a Cepheid in a young, metal-rich galaxy might have a slightly different calibration than one in an older, metal-poor galaxy, requiring careful adjustments and introducing a potential source of error. Furthermore, because they pulse, their brightness is always changing. To get an accurate average, you need to observe them over many cycles, which demands significant and precious telescope time. Then we have the true heavyweights of the distance ladder, Type 1, a supernova. These are not stars in a stable phase, but rather the spectacular, violent deaths of white dwarf stars in binary systems. When a white dwarf accretes enough mass from its companion to reach a critical threshold, it undergoes a runaway nuclear fusion reaction that completely obliterates the star in a thermonuclear explosion. The key here is that this critical mass is always the same, about 1.4 times the mass of our Sun. Because the bomb is always the same size, the peak brightness of these explosions is incredibly uniform, making them visible across billions of light years. They are the rungs on the very top of our cosmic distance ladder, allowing us to measure the expansion rate of the entire universe. But their immense power comes with a significant trade-off. They are transient events. A supernova flares up brilliantly and then fades away over a few months. You get one chance to observe it, and then it's gone forever. You cannot go back and re-measure it. They are also unpredictable. We never know exactly when or where one will occur, so we have to constantly survey vast swaths of the sky hoping to catch one. This is where the quiet, steady reliability of red clump giants truly shines. While Cepheids are brilliant but complex and supernova are spectacular but fleeting, red clump giants are the workhorses of the middle distance range. Their greatest advantage is their sheer prevalence. As we discussed, they are the evolved state of common, sun-like stars which are everywhere. In a typical galaxy, you might find a handful of Cepheids, but you can find thousands upon thousands of red clump giants. This abundance provides a statistical power that single, rare objects cannot match. With so many individual data points, astronomers can average out small random errors and build a much more robust and precise distance measurement for a galaxy. Their stability is another massive benefit. Unlike a Cepheid whose brightness you have to monitor over time, a red clump giant's light output is constant. You can measure it with a single, confident observation. This makes them far more efficient to study, as you don't need to dedicate repeated telescope nights to track their behavior. Perhaps their most underrated advantage is their ability to probe regions of a galaxy that are off-limits to other standard candles. Cepheid variables are young stars, and they are typically found in the spiral arms of galaxies, areas rich with the gas and dust from which new stars are born. But these same spiral arms are also filled with that gas and dust, which can absorb and dim starlight, an effect astronomers call extinction. If you don't account for this dimming caused by dust correctly, you can severely underestimate a star's distance. Red clump giants, being older stars, are not confined to these dusty nurseries. They are found throughout a galaxy, including in its central bulge and in its halo, regions that are often much clearer of obscuring dust. This allows astronomers to measure distances through clearer sightlines, avoiding one of the major headaches in extragalactic astronomy. In essence, red clump giants provide a three-dimensional map of a galaxy's structure, tracing out its bulge, disk, and halo with a uniform grid of points, while Cepheids are mostly limited to mapping the thin, dusty disk. So, while Cepheids and supernova will always be essential for pushing the frontier to the most immense distances, it is the humble, steadfast red clump giant that provides the foundational cartography of our local galactic neighborhood, offering a clarity and reliability that is simply unmatched for building the intermediate steps of our cosmic distance ladder. Now that we understand the theory, how do we actually go about finding these stellar mile markers in the vast sea of the night sky? It's a classic needle in a haystack problem, but modern astronomy has developed some brilliantly effective tools for the hunt. The most fundamental instrument in this search isn't a telescope lens, but a graph. Astronomers rely heavily on what's known as a color magnitude diagram, which is essentially the family tree for stars. To build this diagram for any given star cluster or patch of the galaxy, you need to make two key measurements for each star you see. The first is its color, often expressed as the difference in brightness between two specific wavelengths of light, for instance, blue light versus red light. A star's color is a direct indicator of its surface temperature. Redder stars are cooler, while bluer stars are hotter. The second measurement is its apparent magnitude, which is just how bright it looks from our vantage point on Earth. When you plot tens of thousands of stars on a graph with color on one axis and brightness on the other, patterns emerge that tell the story of stellar evolution. This is where the Red Clump Giants reveal themselves. They don't appear as a random scatter of points. They congregate in a distinct, tight clump at a very specific location on the diagram, in a region with a reddish color and a moderate, consistent brightness. Seeing that dense knot of stars is like spotting a crowd of people all wearing the same color shirt in a massive stadium. They stand out as a coherent group with a shared identity. This clustering is the primary way astronomers identify them. But to get the clean, precise data needed for this kind of discrimination, we need more than just a snapshot. We need a massive, meticulous census of the stars, and that's exactly what missions like the European Space Agency's Gaia Observatory provide. Gaia is a revolution in cosmic cartography. It's not just taking pictures, it's precisely measuring the positions, distances, and motions of over 1 billion stars in our galaxy. Its data allows us to construct color magnitude diagrams of unparalleled precision. With Gaia's help, we can see the red clump not as a fuzzy smudge, but as a sharp, well-defined population. This precise mapping is what allows us to calibrate their true brightness with that remarkable sub-5% certainty, turning a theoretical concept into a practical, high-precision measurement tool. The raw data from surveys like Gaia is phenomenal, but astronomers have another clever trick to make sure they're truly seeing a red clump giant and not an imposter. This involves the sophisticated use of specialized filters on telescopes. Not all red-looking stars are the same. A true red clump giant has a very specific temperature and surface gravity that differentiates it from other types of red stars, like the more luminous and variable red giant branch stars that represent an earlier, less stable phase of life. To tell them apart, scientists use a system of filters that are sensitive to particular bands of light. A very powerful technique involves using 3 specific filters that measure light in the violet, green, and near-infrared parts of the spectrum. The way a star's brightness behaves across these 3 different windows creates a unique signature, a kind of photometric fingerprint. For a red clump giant, the ratio of its brightness in, say, the green filter to its brightness in the near-infrared filter will be distinctly different from that of a red giant branch star, even though they might look similar in a simple red versus blue color measurement. This method is so effective that it can separate the 2 populations with high confidence, even in distant galaxies where we can't get a detailed spectrum for every single star. It's akin to having a special pair of glasses that, when you look at a forest, instantly highlight all the oak trees in green and all the maple trees in yellow, making it trivial to count each type. This photometric identification is a workhorse of modern astronomy because it's efficient. You can observe millions of stars at once through these filters, automatically sift through the data with computer algorithms, and reliably compile a catalog of thousands of red clump giant candidates. This process transforms an overwhelming celestial crowd into a curated list of reliable standard candles, ready to have their distances measured and to begin their work charting the cosmos. All of this theory comes to life in the most personal way possible when we turn our gaze and our telescopes to our own cosmic home, the Milky Way galaxy. For centuries, we were like residents of a vast city, but trapped in a dense fog, able to see the lights of our immediate neighborhood but utterly unable to discern the city's overall layout, its major districts, or its true scale. We knew we lived in a spiral galaxy, but mapping its precise structure from our position inside its disk was an exercise in extreme cosmic guesswork. It's the ultimate insider's problem. When you're embedded within the system you're trying to map, every perspective is limited and every line of sight is cluttered. This is where the legions of red clump giants have become our most effective surveyors. providing a three-dimensional blueprint of our galactic home. Their consistent brightness acts as a universal altimeter, telling us not just how far away a star is, but crucially, whether it sits in the foreground, mid-disk, or all the way in the distant background of the galaxy's central bulge. By measuring the distances to thousands and then millions of these reliable beacons, we can begin to see the architecture of the Milky Way emerge from the stellar fog. One of the most significant contributions has been in tracing the elusive spiral arms of our galaxy. You might think these grand, sweeping structures would be easy to see, but from our vantage point, they are incredibly difficult to pin down. It's like trying to map the shape of a forest by standing in the middle of it. You can see the trees immediately around you, but the overall pattern of hills and valleys is hidden. Spiral arms are not solid structures, but density waves, regions where stars and gas are more densely packed, like a traffic jam on a cosmic freeway. Young, bright stars form in these dense regions and light them up, but they are short-lived and don't provide a stable long-term map. Red Clump Giants, however, are perfect for this task. They are numerous and long-lived, serving as a persistent population that traces the underlying stellar density. By using their distances, astronomers can place them in three-dimensional space. When you plot the positions of hundreds of thousands of these stars, you start to see them clumped together not randomly, but along distinct curving lines that arc across the galactic disk. These are the spiral arms themselves, revealed not by a single bright star, but by the collective glow of a vast population of stellar retirees. This method has allowed us to confirm the position of our own local Orion arm and to measure the scale and pitch of more distant arms like the Perseus and Scutum Centaurus arms, giving us our first truly reliable map of the Milky Way's majestic spiral pattern. Perhaps an even more dramatic revelation has been our ability to measure the true size and shape of the galaxy's central bulge. For a long time, the galactic center was a complete mystery, shrouded by immense clouds of interstellar dust that block almost all visible light. It was like trying to see the heart of a city through a perpetual, thick smog. But red clump giants, especially when observed in near-infrared light that can penetrate that dust, have pierced through this obscuration. By meticulously measuring their distances and positions, astronomers made a startling discovery. The bulge of the Milky Way is not a simple sphere. It has a pronounced boxy or peanut-shaped structure, a shape that emerges from the dynamic orbital resonances of the stars within it. This isn't a static shape, it's a structure that is actively being shaped by the gravitational forces of the galaxy's central bar. The red clump giants allowed us to see this. Their distances revealed that the stars on one side of the bulge are systematically closer to us than the stars on the other side, creating this asymmetric, three-dimensional form. This was a fundamental revision of our understanding of our galaxy's core. We now see it not as a fuzzy, round blob, but as a dynamic, structured, and distinctly non-spherical component. A discovery made possible because we could use these standard candles to gauge depths through the cosmic murk. Beyond the spiral arms and the bulge, these stars are also critical for understanding the larger, more diffuse components of the Milky Way, the stellar halo and the thick disk. Our galaxy is a complex structure of multiple populations. The thin disk where we reside is where most of the young stars and ongoing star formation occur. But enveloping it is a thicker disk composed of older stars, and surrounding that is a vast spherical halo of ancient stars and globular clusters. Red clump giants are found in all of these components. By identifying them and measuring their distances and motions, we can untangle this layered history. A red clump giant in the halo will have a very different motion and chemical composition than one in the thin disk, telling a story of the galaxy's assembly over billions of years. They act as tracers, allowing us to measure the vertical extent of the thick disk and to map the diffuse, sparsely populated halo, revealing the ghosts of smaller galaxies that were cannibalized by the Milky Way in the distant past. This gives us a complete three-dimensional census of our galactic home, from the bustling, star-forming disk to the quiet, ancient outskirts. This entire mapping endeavor was supercharged by the Gaia space mission. Before Gaia, we had a rough sketch. Gaia provided the high-definition survey. By providing exquisitely precise parallax measurements for over 1 billion stars, including countless red clump giants, Gaia gave us the foundational data to calibrate their properties with unprecedented accuracy. But then, to go further, astronomers combined Gaia's data with massive ground-based spectroscopic surveys. These surveys don't just measure a star's distance and brightness, they analyze its light to determine its chemical makeup and its line of sight velocity. When you combine Gaia's precise positions and distances with spectroscopic data, you get a full six-dimensional map, not just where a star is, but how it is moving through space. For red clump giants, this is the final piece of the puzzle. It allows us to see not just the static structure of the Milky Way, but its dynamic architecture. We can watch streams of stars moving together, the remnants of past galactic collisions. We can see the warp and flare of the galactic disk itself, subtle distortions caused by interactions with satellite galaxies. We are no longer just mapping a city, we are watching its traffic patterns, understanding its growth, and predicting its future evolution. The humble, consistent red clump giant in the hands of modern astronomy has become the key that unlocked the detailed blueprint of our own cosmic city, transforming the Milky Way from a mysterious smudge across the sky into a known, measured, and dynamic structure that we are only just beginning to fully comprehend. This incredible three-dimensional map of our galaxy is more than just a static picture, it's a living historical record. By using red clump giants not just as mile markers but as cosmic chronometers, astronomers have unlocked an entirely new field, galactic archaeology. This is the science of digging into the stellar fossil record to piece together the life story of our Milky Way, and these consistent stars are the perfect tools for the excavation. Think of it this way: if you walk into an ancient forest, you can learn about its history by looking at the trees. The oldest, tallest trees tell you about the forest's earliest days, while younger saplings reveal more recent growth. The forest is a living timeline. In exactly the same way, the different populations of stars in our galaxy represent different generations of cosmic growth. And red clump giants are particularly useful trees to study because their properties tell us their age. The key to this dating technique lies in the chemical composition of a star, its metallicity, which is the amount of elements heavier than hydrogen and helium that it contains. In the early universe after the Big Bang, there was only hydrogen, helium, and a tiny trace of lithium. Every other element, the carbon in our bodies, the oxygen we breathe, the iron in our blood, was forged inside the cores of stars and then scattered across space when those stars died in supernova explosions. This means that each successive generation of stars is born from gas that is progressively more enriched with these heavy elements. The very first stars, known as population 3 stars, would have had virtually zero metals. The next generation, population 2, have very low metallicity, and younger stars like our Sun, which is a population 1 star, are quite metal-rich. When we find a red clump giant, we can measure its metallicity by analyzing its spectrum. A red clump giant with low metallicity must be an ancient star, born from the pristine, early material of the universe. A red clump giant with high metallicity is a relative youngster, born more recently from well-processed galactic gas. This connection between metallicity and age transforms every red clump giant we observe into a dated fossil, giving us a way to not only map where the stars are in space, but also to arrange them on a timeline. This powerful combination of distance and age data allows us to perform the true work of galactic archaeology, tracing the merger history of the Milky Way. Our galaxy did not form in isolation. The prevailing cosmological model tells us that large galaxies like ours are built over billions of years through the accumulation and cannibalization of smaller dwarf galaxies. These ancient, shredded galaxies don't just vanish, they leave behind ghostly trails of stars called stellar streams which orbit through the Milky Way's halo. Identifying these streams and dating their stars is like finding the scattered ruins of ancient civilizations within a modern metropolis. Red Clump Giants are perfect for spotting these ruins. Because they are bright, consistent, and easy to date, astronomers can look for large groups of them that share not only a common, distinct metallicity, and therefore a common age, but also a common motion through space. When you find a cohort of ancient, metal-poor red clump giants all moving together on a long, looping orbit that is completely different from the orderly rotation of the main galactic disk, you have almost certainly found the remains of a dwarf galaxy that was consumed by the Milky Way long ago. The most famous example of this is the Gaia Enceladus or Sausage Galaxy, a discovery made possible by data from the Gaia mission. Scientists found that a huge population of stars, including many red clump giants, were moving on highly radial, sausage-like orbits and had a distinct, ancient metallicity signature. This was the clear fingerprint of a massive dwarf galaxy that collided and merged with the infant Milky Way around 10 billion years ago, an event that fundamentally shaped our galaxy's thick disk and halo. Without the ability to reliably identify and date these stellar populations using standard candles like the Red Clump, this monumental event in our galactic history might have remained hidden. Beyond identifying these major mergers, red clump giants help us understand the very process of galactic assembly and evolution. Different parts of our galaxy tell different stories. The central bulge, for instance, is thought to contain some of the oldest stars in the Milky Way, a relic from the initial rapid collapse of primordial gas. By measuring the metallicity and ages of red clump giants in the bulge, we can test this theory. Do they all show uniformly old ages, or is there a mix suggesting a more complex formation history involving both rapid collapse and later mergers? Similarly, the stellar halo is a chaotic graveyard of devoured galaxies, while the thin disk represents the calm, settled region of more recent and continuous star formation. By conducting a systematic census of red clump giants across all these components, the disk, the bulge, and the halo, we can create a detailed timeline of how our galaxy was put together. We can ask and answer profound questions. Did the halo form first? How did the merger with Gaia Enceladus trigger a wave of star formation? How long did it take for the thin, orderly disk to settle into its current form? Each red clump giant is a data point in this grand historical narrative. Their predictable brightness gives us their location, and their chemical fingerprint gives us their birth certificate. By reading these certificates for hundreds of thousands of stars, we are effectively writing the biography of the Milky Way, a story of violent collisions, quiet accretion, and steady evolution over the vast expanse of cosmic time. This isn't just mapping, it's time travel, allowing us to witness the construction of our galactic home, one ancient star at a time. While our detailed map of the Milky Way is a triumph, the true power of this method is revealed when we point our telescopes beyond our own galactic borders toward our nearest neighbors in the local group. This is where red clump giants transition from being local surveyors to becoming cosmic ambassadors, providing the critical link that ties our galactic measurements to the vast scale of the universe at large. The Andromeda Galaxy, a faint, smudged spiral visible to the naked eye on a clear night, has been an object of wonder for millennia, but for astronomers it represented a monumental puzzle. For centuries, we had no true concept of its distance or scale. Was it a small, nearby cloud of gas within our own Milky Way, or a colossal island universe far outside it? This great debate was only settled in the 1920s, but even then, measuring its distance with precision remained incredibly difficult. It was too far for stellar parallax, and other methods carried large uncertainties. This is where the population of red clump giants in Andromeda becomes our Rosetta Stone. Because we have so meticulously calibrated their true brightness within our own galaxy using parallax, we can now confidently identify their counterparts in Andromeda. We look for that same tight clustering on the color magnitude diagram, that same distinct photometric signature. When we find it, we measure how much fainter these stars appear compared to the ones we know in the Milky Way. That precise dimming factor gives us a direct, robust distance to the Andromeda galaxy itself. The answer is staggering. Andromeda is about 2.5 million light-years away. This single measurement, made possible by these stellar standard candles, transforms Andromeda from a mysterious smudge into a known quantity, a galaxy with a defined place in space, a sister system to our own Milky Way whose size and structure we can now accurately compare to our own. The same process is applied to the Triangulum galaxy, another prominent spiral in our local group, allowing us to build a precise three-dimensional map of our immediate cosmic neighborhood. This leap across the intergalactic void is not just about satisfying our curiosity. It is the essential, foundational step for calibrating the entire cosmic distance ladder. The local measurements we make with red clump giants in Andromeda and Triangulum become the solid, reliable anchor point for every other rung on the ladder that reaches deeper into the cosmos. Consider the brilliant Cepheid variable stars. We know their period luminosity relationship is powerful, but to use it with confidence in a distant galaxy, we first need to calibrate it. We need to know the true brightness of a Cepheid with a specific pulsation period. How do we do that? We find Cepheids in a galaxy whose distance we already know independently. Andromeda is that galaxy. Because we have a high-precision distance to Andromeda from its red clump giants, we can observe the Cepheids within it, measure their periods and their apparent brightness, and then, knowing exactly how far away they are, calculate their true, intrinsic luminosity. This cross-calibration is a beautiful piece of scientific symbiosis. The steady, constant light of the red clump giants provides the stable platform from which we can calibrate the pulsating, dynamic light of the Cepheids. Without this local, rock-solid anchor from red clump giants, our understanding of Cepheid brightness would be far shakier, and every distance measurement that relies on them would inherit that uncertainty. The ultimate goal of this entire intricate process is to measure one of the most fundamental numbers in all of cosmology, the Hubble Constant. This constant quantifies the current expansion rate of the universe. It tells us how fast a galaxy is receding from us for every million parsecs of distance. To calculate it, you need two pieces of information for a galaxy: its velocity, which we get from the redshift of its light, and its distance. The farther out we can measure distances accurately, the better we can measure the Hubble constant. This is where the ladder, built on the foundation of red clump giants, extends to its full length. The calibrated Cepheids in Andromeda allow us to measure distances to galaxies far beyond our local group. And in those more distant galaxies, we can find the ultimate standard candles type 1, a supernova. By observing these supernovae in galaxies whose distances are already pinned down by Cepheids, we can calibrate the true peak brightness of these stellar explosions. Once calibrated, these supernovae, visible across billions of light years, become our premier tool for measuring the expansion rate of the universe. Therefore, the humble red clump giant, a star we can study in our backyard, sits at the very base of a chain of measurements that stretches to the cosmic horizon. A small error in the distance to Andromeda, propagated up this entire ladder, would result in a significant error in the Hubble constant. The remarkable precision we now have with red clump giants, with uncertainties of just a few percent, tightens the entire ladder, reducing the systematic errors and allowing for a much more precise and accurate determination of how fast our cosmos is growing. This ongoing refinement is critically important because it places us at the heart of a major modern cosmological mystery. Different methods of measuring the Hubble constant are now yielding subtly but persistently different results. The value derived from the cosmic distance ladder, the method that starts with red clump giants and Cepheids and ends with supernova, disagrees with the value predicted from the pristine conditions of the early universe as measured by the Planck satellite. This discrepancy, known as the Hubble tension, suggests that there might be something fundamental we are missing about the universe, perhaps a new type of particle or a previously unknown property of dark energy. In this high-stakes scientific detective story, the role of the Red Clump Giant is to act as a reliable witness. By continually refining their properties and cross-checking their distances with other independent methods within the Milky Way and local group, astronomers are stress-testing the very first rung of the ladder. They are asking, is our local anchor truly solid? The consensus, built from vast datasets from missions like Gaia, is that it is. This gives greater weight to the distance ladder measurement and intensifies the mystery of the Hubble tension. It suggests that the discrepancy is not due to a local measurement error, but may indeed point to new physics. So, the quiet, consistent burning of a red clump giant does more than just light up a distant galaxy. It illuminates a potential pathway to a deeper understanding of the universe's fundamental laws, proving that even the most local cosmic phenomena are inextricably linked to the grandest questions about the nature of reality itself. The role of red clump giants in measuring the Hubble constant is a perfect example of how a local, meticulous measurement reverberates across the entire cosmos, influencing our understanding of the universe's ultimate fate. This all traces back to that foundational cosmic distance ladder. Remember, the ladder begins with parallax measurements of nearby stars which calibrate the red clump giants. Those giants then provide a precise distance to galaxies like Andromeda, which in turn calibrates the brighter Cepheid variables. And finally, those Cepheids measure distances to galaxies far enough away to host Type 1, a supernova, calibrating those brilliant explosions for the final leap to the edge of the observable universe. The Hubble constant, represented as h0, is the final product of this entire meticulous process. It's the number that tells us how fast the universe is expanding today. For every million parsecs of distance, a galaxy recedes from us at a velocity of h0 kilometers per second. To get that number, you need two things for a set of distant galaxies: their velocity, which we get easily from the redshift of their light, and their distance, which is the hard part. This is where the ladder, built upon the trusty foundation of red clump giants, delivers the crucial data. The incredible precision we now have with these stellar mile markers, with uncertainties of just a few % for nearby galaxies, means the first rung of the ladder is exceptionally solid. This precision propagates upward, reducing systematic errors at every subsequent step. When astronomers finally use calibrated supernova to measure distances to galaxies billions of light-years away, they can plot a Hubble diagram: distance versus velocity, and the slope of that line is the Hubble constant. A steeper slope means a faster expanding universe. A shallower slope indicates a more leisurely pace. The value derived from this cosmic distance ladder method is therefore one of the most direct measurements we have of the universe's current expansion rate. It's a measurement rooted in the empirical, step-by-step observation of celestial objects, a bottom-up approach that starts in our galactic backyard and reaches out to the cosmic horizon. The consistency of red clump giants ensures that this entire intricate structure doesn't wobble at its base, giving us great confidence in the final result. This result, however, has placed cosmology at a fascinating and somewhat tense crossroads. For decades, we assumed that by measuring the universe's expansion in different ways, we would arrive at the same answer. But nature, it seems, has a surprise for us. When we compare the Hubble constant value from the distance ladder to the value predicted from observations of the early universe, a clear and persistent discrepancy emerges. The early universe method relies on the afterglow of the Big Bang, the cosmic microwave background, as exquisitely mapped by satellites like Planck. The patterns in this ancient light allow us to extrapolate forward using our well-tested model of cosmology to predict what the expansion rate should be today. The problem is the two numbers don't match. The distance ladder method, anchored by Red Clump Giants and Cepheids, gives a higher, faster value for the Hubble Constant. The early universe method, based on the cosmic microwave background, gives a lower, slower value. This disagreement is known as the Hubble tension, and it has become one of the most significant puzzles in modern physics. It's not a small, marginal error. It's a discrepancy that has persisted and even grown with more precise data, now standing at a level of significance that is very hard to ignore. This is where the humble red clump giant plays a role far grander than its stellar nature might suggest. In this high-stakes debate, they act as the reliable witness for the local measurement. Critics and researchers alike have asked, could the tension simply be due to an unknown error at the bottom of the distance ladder? Perhaps our calibration of Cepheids or even red clump giants themselves has a hidden flaw. This is where the sheer abundance and cross-checked reliability of red clump giants become a powerful defense. Astronomers have used multiple independent methods, including eclipsing binaries and other geometric techniques, to verify the distances to red clump giants in our galaxy. The data from the Gaia mission has provided a colossal dataset that confirms their properties with overwhelming statistical force. This robust verification strongly suggests that the first rung of the ladder is not broken. The local measurement appears to be sound, which lends immense credibility to the higher expansion rate found by the distance ladder method. This, in turn, intensifies the Hubble tension, making it increasingly likely that the discrepancy is not a measurement error but a clue. It could be pointing towards something missing from our standard model of cosmology, perhaps a new type of dark energy that behaved differently in the past, or a new species of neutrino, or some other exotic physics that we have not yet discovered. The quiet, steady glow of millions of red clump giants across the Milky Way and local group thus finds itself at the center of a revolution. They provide the stable, trusted data point that allows us to confidently challenge our most fundamental theories about the universe. Their role transforms from mere distance markers to essential keys in a cosmic lock. A lock that, once opened, may reveal a deeper and more complete understanding of the forces that have shaped and continue to shape the entirety of existence. However, for all their remarkable reliability, red clump giants are not a perfect tool, and their use comes with a set of significant challenges that astronomers must constantly work to overcome. The very cosmic dust that helps form stars also conspires to hide them, presenting one of the most persistent obstacles: interstellar extinction. This isn't about a star fading away. It's about its light being absorbed and scattered by the vast clouds of microscopic dust grains that drift through the space between stars. Think of trying to see the beacon of a lighthouse on a foggy night. The light is still just as powerful, but the fog dims and reddens it, making it appear farther away than it truly is. This is precisely what happens to starlight. Dust acts as a cosmic fog, selectively scattering blue light more than red light, which not only makes the star appear dimmer but also makes it look redder. For a red clump giant, which is already a red star, this poses a serious problem. If we simply measure how faint it appears and assume that dimming is solely due to distance, without correcting for the dimming from dust, we will severely overestimate how far away it is. Our cosmic mile marker would be giving us a false reading. Correcting for this extinction is a complex and critical step. Astronomers often use multi-wavelength observations, measuring the star's brightness in several different colors, like blue, visual, and infrared. The amount of dimming and reddening across these different bands reveals the properties of the intervening dust, allowing scientists to calculate a correction factor and recover the star's true, undimmed apparent brightness. It's a delicate and essential piece of cosmic forensics, without which our entire three-dimensional map of the galaxy would be systematically distorted, like a building where every measurement is just a little bit too long. A more subtle but equally important challenge comes from the chemical composition of the stars themselves, specifically their metallicity. While the core helium burning process that powers Red Clump Giants is wonderfully consistent, the overall structure and atmosphere of the star can be influenced by the abundance of elements heavier than hydrogen and helium. A star with high metallicity, meaning it formed from gas enriched with many heavy elements, will have a slightly different internal opacity and atmospheric structure compared to a star with low metallicity that formed from more primordial material. This difference can translate into a small but systematic shift in the star's true intrinsic brightness. A high metallicity red clump giant might be a few percent brighter than a low metallicity one. In a mixed population of stars, like the halo of our galaxy where metallicities can vary wildly, this introduces a spread in the standard candle's wattage. If we were to treat all red clump giants as having exactly the same brightness, we would introduce noise and systematic errors into our distance measurements. The low metallicity stars would appear closer than they are, and the high metallicity stars would seem farther. To combat this, astronomers must become stellar chemists. By taking a spectrum of a red clump giant, they can measure its metallicity and then apply a small correction to its assumed luminosity based on established calibration relations. This refinement is crucial for achieving the highest possible precision, especially when using these stars to probe the outer, metal-poor regions of galaxies or to compare distances between galaxies with different chemical histories. It's a reminder that nature rarely provides a one-size-fits-all solution, and that our most powerful tools often require careful, nuanced calibration. Perhaps the most practical observational hurdle is the problem of crowding, especially when we look toward the centers of galaxies or dense star clusters. From our distant vantage point, the core of a galaxy like Andromeda appears as a seething, incredibly dense metropolis of stars. Individual points of light blur together into a glowing continuum. Trying to pick out a single, specific red clump giant in such a crowded field is like trying to identify one particular person in a densely packed stadium from a mile away using a telescope. The light from the target star blends with the light from its many neighbors, an effect astronomers call blending. This contamination artificially inflates the measured brightness of the star. If we mistake this blended, overly bright light for the true light of our standard candle, we will think the star is closer than it actually is. Our distance measurement would be compromised. Overcoming this requires both technological and analytical sophistication. Space telescopes like Hubble, with their sharp vision, are invaluable for resolving these dense stellar fields. Advanced computer algorithms are then used to model the light distribution of each star in the image, carefully separating the flux of the red clump giant from the surrounding fog of its neighbors in a process known as point spread function fitting. It's a painstaking task, but a necessary one to ensure that the signal we are measuring is pure and uncontaminated, preserving the integrity of our cosmic ruler. Finally, there is the challenge of simply knowing for certain that you're looking at a genuine red clump giant and not an imposter. The stellar family tree has several branches that pass through similar regions of the color magnitude diagram. A particular pitfall is distinguishing a true core helium burning red clump giant from a star on the red giant branch that is still burning hydrogen in a shell. These shell-burning giants can have similar colors and can even appear at similar brightness levels, but they are not in a stable evolutionary phase and do not share the same predictable luminosity. If we accidentally include these interlopers in our sample, we introduce a population of stars with a much wider range of brightness, corrupting the clean standard candle signal. This is where the advanced filtering techniques and detailed spectroscopic analysis become non-negotiable. By using those specific photometric fingerprints or by measuring the star's surface gravity from its spectrum, a property that is different for a red clump giant than for a shell-burning giant, astronomers can perform a stellar identity check, weeding out the imposters and ensuring that their final catalog contains only the most reliable distance indicators. Acknowledging and meticulously accounting for these limitations is not a sign of weakness in the method, but a testament to the rigor of modern astronomy. It is through this constant process of identification, correction, and refinement that the humble red clump giant is transformed from a good idea into a precision instrument for mapping the cosmos. But what if we had a way to peer directly into the heart of a red clump giant, to test its internal physics and measure its properties without relying on any external calibrations? This isn't science fiction, it's the revolutionary field of asteroseismology, and it's providing the most rigorous independent check possible on these cosmic mile markers. Asteroseismology is the study of stellar oscillations, the natural, rhythmic pulsations that occur in nearly all stars. Think of it as stellar seismology, akin to how geologists use earthquakes to probe Earth's interior. Stars are not silent, static orbs. They ring like gigantic bells. Convection in their outer layers continuously excites sound waves that travel through the stellar interior, causing the entire star to expand and contract in a complex symphony of vibrations. These pulsations are incredibly subtle, often causing the star's brightness to fluctuate by mere fractions of a percent, but they encode a wealth of information about the star's internal conditions. For red clump giants, this seismic music is particularly rich and revealing. The specific patterns of oscillation, the frequencies at which the star naturally vibrates, are directly tied to its fundamental properties. The most accessible rhythm is the large frequency separation, which is the regular spacing between oscillations of the same harmonic degree. This spacing is intimately related to the star's average density. A higher average spacing means a denser, more compact star. A lower spacing indicates a larger, more puffed-up star. Since a star's radius and mass determine its average density, measuring this frequency separation allows astronomers to solve for both values with astonishing precision. It's like being able to weigh and measure a star simply by listening to the unique song it sings. This seismic analysis provides a powerful, direct test of the very foundation that makes red clump giants such reliable standard candles, their consistent luminosity. Recall that their predictable brightness stems from the idea that they all have very similar helium-burning cores under degenerate conditions. Asteroseismology allows us to verify this claim by directly measuring the mass of these stars. When scientists analyze the oscillation spectra of thousands of red clump giants, they find a remarkable confirmation. The masses overwhelmingly cluster around a very narrow range, typically between 0.8 and 1.2 times the mass of our Sun. This tight distribution is exactly what the theory of the helium flash predicts. Stars outside this mass range either never become red clump giants or they evolve through this phase too quickly to be numerous. This seismic weighing scale provides empirical, ironclad evidence that we are indeed dealing with a homogeneous population of stars, all engineered by nature to the same fundamental specifications. Furthermore, the oscillation modes can probe the internal structure, distinguishing between a star that is burning helium in its core and one that is merely burning hydrogen in a shell. This helps weed out any potential imposters, ensuring that the samples used for distance measurements are seismically pure. This independent validation is crucial for silencing any lingering doubts about the method's reliability. We are no longer just assuming these stars are standard. We are using the physics of their own vibrations to prove it. The ultimate application of this technique is in measuring distances entirely independently of the cosmic distance ladder. This is where asteroseismology moves from being a validation tool to becoming a primary measurement method in its own right. The process combines several seismic measurements. First, the large frequency separation gives us the star's average density. Second, another set of oscillations, particularly sensitive to the conditions in the stellar core, gives us the frequency of maximum power, which relates to the star's surface gravity and effective temperature. By combining the average density with the surface gravity, astronomers can directly calculate the star's radius. It's a purely physical deduction from the oscillation frequencies, with no reliance on knowing how far away the star is. Once you know the star's true physical radius and its surface temperature, you can calculate its true intrinsic luminosity using the fundamental laws of blackbody radiation. You now know the star's actual wattage, derived entirely from its own seismic signature. The final step is the same as for any standard candle. Compare this known true luminosity to the star's apparent brightness as seen from Earth, and you solve for distance. This asteroseismic distance is completely independent of parallax, of galactic models, and of any other rung on the traditional cosmic distance ladder. It's a direct, one-step measurement rooted in the fundamental physics of the star itself. The power of this approach was spectacularly demonstrated by data from the Kepler Space Telescope. Kepler's primary mission was to find exoplanets by staring relentlessly at one patch of sky, measuring the tiny dimming caused by planets passing in front of their host stars. This same ultra-precise, continuous photometry was a goldmine for asteroseismology. For the first time, scientists could detect the minute oscillations of thousands of red clump giants with incredible clarity. This led to a beautiful convergence. Distances to these stars measured seismologically showed exquisite agreement with the distances measured by the Gaia satellite using parallax. This independent verification from two completely different physical methods, one geometric, one seismic, cements our confidence in the entire measurement chain. Asteroseismology doesn't replace the red clump method, it elevates it. It transforms these stars from being simply reliable to being fundamentally understood. We are no longer just using them as tools, we are conversing with them, listening to the subtle vibrations that reveal their deepest secrets, and in doing so, we are fortifying the very foundation of our map of the universe. This dialogue between stellar physics and cosmic measurement ensures that the distances we rely on to understand everything from the structure of our galaxy to the expansion rate of the cosmos are built on the most solid, multifaceted, and trustworthy foundation that modern science can provide. All of this theoretical understanding and painstaking correction for dust and metallicity would be for nothing if we didn't have the raw data to fuel it. For decades, the study of red clump giants was like trying to map a continent with only a handful of scattered landmarks. We had a rough sketch, but the fine details, the true topography, remained hidden. This all changed in a revolutionary way with the launch of the European Space Agency's Gaia mission. Gaia is not just another telescope, it is a paradigm-shifting observatory, a cosmic census bureau whose sole purpose is to measure, with breathtaking precision, the positions, distances, and motions of over 1 billion stars in our galaxy. Think of it as giving the entire field of astronomy a new pair of glasses, one that corrects for a blurry, nearsighted view and replaces it with a vision of stunning, high-definition clarity. Before Gaia, our best catalogues contained parallax measurements for maybe a few tens of thousands of stars, and even those had significant margins of error at larger distances. Gaia has turned this trickle of data into a tidal wave. It has provided exquisitely precise parallax measurements not just for a few, but for millions of red clump giants, transforming them from a well-understood class of objects into a finely calibrated army of individual distance markers. This incredible dataset allows for a calibration of their properties that was previously unimaginable. Remember, the entire value of a standard candle rests on knowing its true brightness with certainty. Before Gaia, we had to infer this true brightness from statistical studies of star clusters or from a small number of local stars with less precise parallax. It was a bit like trying to determine the exact height of an average person by looking at a crowd from a mile away. With Gaia, we can now walk right up to millions of individual people and measure their height with a ruler. By directly measuring the distance to a red clump giant via parallax and simultaneously measuring its apparent brightness from Earth, we can perform a simple calculation to determine its true, intrinsic luminosity with minimal assumptions. The result of this mammoth calibration effort has been a resounding confirmation of their reliability. The data shows a tight, unmistakable clustering of luminosity for these stars with a spread of less than 5%. This isn't just a theoretical prediction anymore, it's an empirical fact backed by the most extensive and precise geometric measurements ever conducted. This has elevated the red clump method from a useful technique to a gold standard for intermediate distance measurements. The impact on galactic cartography has been nothing short of breathtaking. With millions of these precisely calibrated mile markers scattered throughout the Milky Way, we have moved from drawing a simple outline of our galaxy to constructing a dynamic, three-dimensional model. Imagine trying to understand the structure of a city using only a flat, two-dimensional map. You might see where the streets are, but you'd have no sense of the hills, the valleys, or the towering skyscrapers. Gaia's data on red clump giants has given us the third dimension depth. We can now see that our galaxy's disk is not flat like a pancake, but warped like a vinyl record left in the sun. This warp, likely caused by gravitational interactions with satellite galaxies, is now mapped in exquisite detail, showing how the outer edges of the disk twist and bend. Furthermore, we can see that the disk itself has a vertical structure, with a thin disk where younger stars like our Sun reside, and a thicker disk of older stars, all traced out by the distinct populations of red clump giants. We can measure the flare of the disk where it gets thicker towards the outer regions, and we can see the ghostly imprints of past galactic collisions in the form of stellar streams weaving through the halo, each stream populated by its own cohort of ancient red clump giants. This is no longer just a map, it's a living, breathing portrait of a dynamic galaxy, and it is being painted stroke by stroke with the data from these trusted stellar beacons, all made possible by the transformative precision of the Gaia mission. The meticulous work of mapping our local universe with red clump giants has been a monumental achievement, but it is merely the prelude to an even grander era of discovery. The next revolution in cosmic cartography is already underway, propelled by a new generation of observatories that will turn these reliable standard candles into probes for the most distant and enigmatic corners of the cosmos. Leading this charge is the James Webb Space Telescope, an instrument that sees the universe in infrared light. For red clump giants, this is a game changer. Interstellar dust, which has long been the nemesis of precise distance measurements, is virtually transparent to Webb's infrared eyes. This means we can now peer directly into the crowded, dusty hearts of distant galaxies and identify red clump giants with crystal clarity. Previously, the central regions of galaxies like Andromeda were a blur, their stars blended into a single glowing mass. With Webb, we can resolve individual red clump giants right to the very core, measuring their brightness without the crippling effects of dust extinction. This allows us to construct a complete, three-dimensional map of a galaxy's bulge and nucleus, regions that hold the key to understanding how galaxies first assembled. Furthermore, Webb's incredible spectroscopic power lets us analyze the chemical composition of these distant giants with unprecedented precision. We'll be able to measure their metallicity not as a broad average, but for thousands of stars individually, tracing the complex chemical history of galactic building blocks across space and time. This transforms them from simple distance markers into detailed fossils, each one telling a story about the conditions in its host galaxy billions of years ago. Joining Webb in this celestial census will be the Nancy Grace Roman Space Telescope, a wide-field survey machine with a field of view over 100 times larger than that of the Hubble Space Telescope. While Webb is a powerful magnifying glass for detailed study, Roman is a panoramic camera designed to capture the big picture. Its primary mission will be to conduct vast, deep surveys of the sky, and in the process, it will automatically capture photometric data for hundreds of millions of red clump giants across thousands of galaxies. This staggering volume of data will move us from case studies to universal statistics. Instead of carefully measuring the distance to one galaxy at a time, we will be able to construct a three-dimensional map of the entire local universe, a cosmic web of galaxies whose positions are pinned down with red clump precision. This map will reveal the large-scale flow of galaxies, the subtle tides and currents driven by dark matter, and the true distribution of matter on the grandest scales. Roman's wide-field infrared capabilities also make it ideal for studying red clump giants in the dim, low metallicity dwarf galaxies that orbit larger ones like our Milky Way. These pristine galactic fossils are crucial for testing our models of galaxy formation, and Roman will find and measure their stellar populations in overwhelming numbers, providing a definitive demographic survey of our cosmic neighborhood. On the ground, the Vera C. Rubin Observatory will complement these space-based giants with its own relentless all-sky survey. Equipped with the largest digital camera ever built, Rubin will scan the entire visible sky every few nights, creating a dynamic 10-year movie of the cosmos. For red clump science, this temporal dimension is a new frontier. While an individual red clump giant is stable, observing vast populations of them over time allows for a different kind of science, precision proper motion studies on an extragalactic scale. By tracking the tiny, year-to-year shifts in the positions of red clump giants in a galaxy like Andromeda, Rubin will allow us to measure their collective motion through space. This gives us the galaxy's proper motion, a crucial piece of kinematic data that, when combined with the distance from the stars themselves, reveals the full three-dimensional velocity of our nearest galactic neighbor. This will finally allow us to understand the past and future orbital dance between the Milky Way and Andromeda with supreme accuracy. Moreover, Rubin's rapid-fire observations will be a factory for asteroseismology. By monitoring the minuscule brightness variations of millions of red clump giants, it will detect the resonant pulsations that allow for direct seismic distance measurements. Rubin will essentially perform asteroseismology on an industrial scale, providing independent distance checks for countless galaxies simultaneously and further solidifying the foundation of the entire cosmic distance ladder. The combined power of these observatories will also push the effective range of the red clump method to new limits. Currently, they are workhorses for the local group and a bit beyond. But with the enhanced resolution and sensitivity of Webb and Roman, we will be able to identify and cleanly measure red clump giants in galaxies tens of millions of light-years away. This extends the direct primary rung of the distance ladder deep into the universe, reducing our reliance on the more complex and potentially uncertain calibrations of Cepheid variables for a much larger volume of space. This has a direct and profound impact on the Hubble tension. By using red clump giants to directly anchor the distances to more galaxies that also host Cepheids and Type 1a supernova, we can test the distance ladder for systematic errors at multiple points. If the tension persists even with this more robust, red clump-heavy calibration, the evidence for new physics becomes overwhelming. These stars will be at the forefront of either confirming our standard model of cosmology or forcing a radical rewrite. Ultimately, this new era is about moving from static maps to dynamic, evolutionary understanding. We will no longer just know where a galaxy is. We will know how it moves, how it assembled, and what its chemical history has been, all read from the light of its most common and reliable stellar citizens. The data from these telescopes will be so vast that machine learning algorithms will be essential for sifting through the haystack of stars to find every single red clump needle, building catalogs of such size and precision that our current maps will look like rough sketches by comparison. The humble red clump giant, a predictable phase in the life of an average star, is about to become the key that unlocks the next great chapter in our understanding of the universe's structure, history, and ultimate fate, proving that sometimes the most powerful tools are not the rarest or the most exotic, but the ones we can find almost everywhere we look. But this journey through stellar evolution and cosmic mapping raises a deeply personal question. What happens to the planets that might orbit these aging suns? Our exploration of red clump giants as celestial lighthouses is complete, but their story as potential homes for worlds is just beginning, a story that directly involves the ultimate fate of our own solar system. When a star like our Sun exits the main sequence and balloons into a red giant, its transformation is not a gentle one. Its outer layers expand outward by a staggering amount, swelling to engulf the inner solar system. For a star becoming a red clump giant, this means the orbits of Mercury and Venus are certainly consumed, and Earth's fate hangs in the balance, a precarious question of whether the expanding stellar atmosphere will reach our orbit or if our planet will merely be scorched beyond recognition. This isn't just a theoretical doom for distant worlds. It's the prophesied end for our own, a dramatic demonstration of how the death of a star fundamentally rewrites its planetary system. The search for planets around red clump giants, therefore, becomes a form of cosmic archaeology, digging through the aftermath of this stellar upheaval to understand which worlds can survive and what new, exotic worlds might be born from the chaos. The process of a star engulfing its inner planets is as violent as it is inevitable. As the star's outer envelope expands, it doesn't simply push planets away. It envelops them, subjecting them to intense drag forces within a thick, hot plasma. A planet like Earth would not be vaporized instantly, but would spiral inward over a period of thousands of years, its orbit decaying as it plows through the tenuous outer layers of the star. During this death spiral, the planet would experience unimaginable heating, its surface melting and then boiling away, its very substance being stripped layer by layer and added to the star's composition. This process can actually pollute the star's atmosphere with the heavy elements that were once part of the planet, leaving a detectable chemical signature. Astronomers can sometimes see an overabundance of elements like lithium or certain refractory metals in the spectra of red clump giants, a potential ghostly fingerprint of a devoured world. This ingestion also transfers angular momentum to the star, potentially causing it to spin up rapidly. Finding a red clump giant that is rotating faster than expected is another tantalizing clue that it may have recently consumed a substantial planetary companion, a last meal before settling into its stable retirement phase. Yet, against all odds, planets do exist in these evolved systems. The hunt for these post-apocalyptic worlds has yielded surprising discoveries, primarily gas giants orbiting at a safe distance. Imagine a Jupiter-like planet originally orbiting its star at a distance of 500 million miles. When the star swells, it may only reach out to the orbit of Mars or the asteroid belt, leaving that distant Jupiter unscathed, though now bathing it in a much more intense radiance. Astronomers have detected such planets around red clump giants using the radial velocity method, which looks for the subtle wobble a planet's gravity induces in its host star. These detections are crucial because they tell us that not all planets are destroyed. The architecture of planetary systems is permanently altered. The inner terrestrial worlds are gone, but the outer gas giants remain, their orbits potentially altered by the star's mass loss during its red giant phase. As a star sheds its outer layers, it loses a significant fraction of its mass, which weakens its gravitational grip on the entire system. This can cause the surviving outer planets to migrate outward, settling into wider, more distant orbits. We are essentially seeing the final configuration of planetary systems, a glimpse of what our own solar system will look like long after Earth is gone. This leads to one of the most intriguing possibilities, the potential for second-generation planets, the material ejected from a star during its late evolution. The beautiful planetary nebulae that are the star's final shroud is rich in heavy elements. This processed material, along with the debris from shattered inner planets, can form a new circumstellar disk of dust and gas around the remaining stellar core, which will eventually become a white dwarf. Within this disk, a process of planet formation could potentially start all over again. While forming large gas giants might be unlikely, the creation of new, rocky worlds is a fascinating possibility. These would be planets born from the ashes of their predecessors, worlds with compositions utterly different from the first generation that formed with the star billions of years earlier. While this is more directly associated with the white dwarf phase that follows the red clump, the initial dispersal of material begins during the giant phases. Discovering such a second-generation planet would be a monumental find, revealing planetary system evolution as a cyclical process of death and rebirth on a cosmic scale. For us, the most profound implication lies closer to home. Studying red clump giants and their planets holds up a mirror to our own distant future. Our Sun has a little over 5 billion years left on the main sequence before it too will swell into a red giant and pass through its own red clump phase. The detailed observations of these stellar retirees allow us to run a cosmic simulation, to see with our own eyes the processes that will one day determine the fate of our world. By measuring how large different stars become, we can refine our models of just how far the Sun's atmosphere will reach. By finding the chemical evidence of engulfed planets in other stars, we can better understand the physical processes that will dismantle our own planet. And by discovering the surviving gas giants in these systems, we get a preview of what will become of Jupiter, Saturn, and their moons, transformed from icy worlds orbiting a distant sun to potentially warmer bodies bathing in the intense, though temporary, glow of a giant star. The search for planets around red clump giants is therefore more than an astronomical curiosity. It is a form of time travel, allowing us to peer billions of years ahead and read the final chapter of our solar system story, a chapter written in the light of stars that have already reached the end we have yet to face. This entire process of using red clump giants as cosmic measuring tapes ultimately loops back to a profoundly important cycle. The data we collect from them doesn't just use our theories of stellar evolution. It actively refines and stress tests those very theories. Think of it as a continuous conversation between observation and prediction. Astrophysicists build incredibly sophisticated computer models that attempt to simulate the entire life of a star, from its birth in a cloud of gas to its final demise. These models are based on our best understanding of fundamental physics, the equations of nuclear fusion, the principles of hydrostatic equilibrium, and the complex mechanics of how energy moves from a star's searing core to its shimmering surface. But a model is only as good as its predictions. We can run these virtual stars on a supercomputer, but we need real-world data to tell us if we've gotten the physics right. This is where the red clump giants become the ultimate exam proctors. Their well-defined properties, which we measure with such precision, provide a strict set of answers that our models must match. One of the most critical tests involves the star's mass and its resulting luminosity. Stellar evolution theory makes a very specific prediction. For a population of stars with similar chemical composition, the final luminosity of a red clump giant should be tightly correlated with its initial mass on the main sequence. It's a direct consequence of the helium flash happening under degenerate conditions, which effectively erases the memory of small differences in initial mass, forcing them all into a similar brightness. So, when astronomers use data from missions like Gaia to measure the masses and luminosities of thousands of real red clump giants, They can hand this dataset to the theorists and ask, does your model produce this same tight clustering? The answer has been a resounding yes, but with fascinating nuances. The models successfully predict the general brightness of the clump, but subtle discrepancies often emerge around the edges. For instance, the observed population might be slightly brighter or fainter than predicted for stars of a certain metallicity. These tiny mismatches are not failures, they are gold mines. They point directly to physical processes in the models that might be slightly off, such as the precise rate of nuclear reactions in the helium-burning core or the efficiency of a process called convective overshooting, where bubbling currents of plasma from the core penetrate slightly further into the surrounding layers than simple models assume. The internal structure of these stars, particularly the size and mass of their helium-burning cores, is another area where theory meets observation head-on. The models calculate exactly how much helium must be fused into carbon and oxygen to trigger the flash and subsequently sustain stable burning. This predicts a specific core mass. But how do you measure the core of a distant star? This is where the seismic data from asteroseismology becomes utterly invaluable. The oscillation modes detected by telescopes like Kepler are exquisitely sensitive to the conditions in the stellar interior. Certain oscillation patterns can literally probe the boundary between the helium-burning core and the hydrogen-burning shell that surrounds it. By analyzing these frequencies, astronomers can effectively weigh the core and measure its radius. When they compare this seismically measured core mass to the value predicted by the standard stellar models, they often find a small but significant disagreement. The real stars seem to have slightly more massive cores than the models predict. This discrepancy is a major clue. It suggests that our understanding of how material mixes at the edge of the core might be incomplete. Perhaps there are additional mixing processes driven by rotation or internal waves that are slowly feeding extra helium fuel into the core, making it more massive and therefore slightly altering the star's energy output. Identifying this flaw pushes modelers to go back and incorporate more complex, realistic physics into their simulations, leading to a new generation of models that more accurately reflect the turbulent, dynamic interior of a real star. This iterative process of prediction, observation, and refinement is the very engine of scientific progress in astrophysics. The red clump phase acts as a magnifying glass held over the later stages of stellar life. Because these stars are in such a stable and well-defined state, any deviation between what we see and what we calculate stands out clearly. This helps physicists refine not just our picture of stellar old age, but fundamental parameters that affect all stars. For example, the opacity of stellar material, how effectively it absorbs and re-radiates light, is a crucial factor in any model. If the opacity in our models is slightly too high or too low, energy will not transport through the star correctly, and the model's predicted temperature, size, and brightness will be wrong. The precise luminosity and color of red clump giants provide a stringent test for these opacity tables. Similarly, the nuclear reaction rates for the fusion of helium into carbon, a process known as the triple alpha process, can be constrained. If the models need to be adjusted to match the observed properties of the clump, it gives nuclear physicists feedback on the behavior of matter under these extreme densities and temperatures. Ultimately, the humble red clump giant is more than a tool for mapping space. It's a laboratory for probing the laws of physics under conditions we could never recreate on Earth. Each one is a natural experiment, a self-contained fusion reactor that has been running for billions of years. By carefully observing its light, its vibrations, and its composition, we are effectively reading the output of that experiment. The sophisticated computer models are our attempt to write the theory that explains that output. Every time we find a mismatch, we learn something new. We discover a previously ignored physical process, we refine a nuclear cross-section, or we improve our treatment of how energy flows through a seething plasma. This constant dialogue ensures that our theories don't remain abstract mathematical exercises, but are grounded in the reality of the stars themselves. The reliable light of the Red Clump Giants therefore illuminates not just the vast distances between galaxies, but also the deepest workings of the universe's fundamental forces, guiding us toward an ever more complete and accurate understanding of how stars are born, live, and die. Now, let's journey from the calm outskirts of galaxies into their chaotic, vibrant hearts, the galactic centers. This is a realm of extremes where stars are packed together in a dazzling, crowded metropolis, all orbiting an invisible and unimaginably dense monster, a supermassive black hole. In this frenetic environment, you might expect the orderly rules of stellar evolution to break down, yet here, the resilient Red Clump Giants are not just present, they are thriving, acting as our most reliable guides to this otherwise impenetrable region. Studying this unique population is like sending hardened scouts into a storm. They withstand the gravitational turmoil and intense radiation, and by simply doing what they do best, shining with predictable brightness, they reveal the deepest secrets of galactic nuclei, from their violent formation history to the bizarre physics happening at the edge of spacetime itself. The first challenge in understanding these central regions is simply seeing through the cosmic smog. Galactic centers are shrouded in thick clouds of gas and dust, blocking most visible light from ever reaching our telescopes. It's like trying to observe the details of a city's downtown through a dense, perpetual haze. This is where the Red Clump Giants' natural affinity for infrared light becomes a superpower. Their reddish glow, which indicates a cooler surface temperature, is predominantly emitted in the infrared part of the spectrum. And infrared light has a magical property. It can pierce through that obscuring dust. When we point powerful infrared telescopes like the James Webb Space Telescope toward the heart of our own Milky Way, the fog lifts. Suddenly, we can resolve individual stars in the crowded stellar metropolis surrounding our supermassive black hole, Sagittarius A. And a significant portion of these resolved stars are unmistakably Red Clump Giants. Their distinctive, tight clustering on the color magnitude diagram shines through clearly, even from 26,000 light-years away. This allows us to do something extraordinary. We can count them, measure their brightness, and use them to construct a three-dimensional map of the galactic center. We can see how they are distributed, whether they form a flattened disk or a more spherical swarm. And this structure itself tells a story about how the central region was assembled. Their predictable light provides the ruler we need to measure the true scale of the central bulge and the distance to the black hole itself with remarkable precision, cutting through the cosmic murk that has hidden the galaxy's core for centuries. But why are they there in such numbers? The presence of a vast population of Red Clump Giants in the galactic center is a clue to an ancient and violent history. These stars are old. They are the evolved descendants of sun-like stars that must have formed billions of years ago. Their sheer abundance suggests that the galactic center experienced a tremendous, explosive burst of star formation in the distant past, creating a vast swarm of stars all at once. Imagine a single epic event where millions of stars ignited in a short cosmic time span. Fast forward billions of years, and all those stars that started with similar masses are now reaching the same point in their evolution, the red clump phase, simultaneously. This is why we see such a prominent, dense clump of them. They are a living fossil record of that initial starburst. However, the environment they inhabit is anything but peaceful. They are living their retirement years in a gravitational maelstrom, subjected to the relentless pull of the central black hole and the chaotic jostling of countless neighboring stars. This extreme environment leaves its mark. Astronomers can study the motions of these red clump giants, tracing their orbits around the black hole. Some may be on stable, circular paths, while others could be on wildly eccentric orbits, flung around by close encounters with other stars. By mapping their movements, we can literally weigh the central black hole. The The speeds and paths of these orbiting giants are dictated by the mass of the invisible object they circle, providing the most direct evidence for the immense gravitational anchor at the galaxy's heart. The most fascinating red clump giants, however, are those that dare to venture into the innermost sanctum, the region so close to the black hole that the laws of physics as we know them begin to warp. Here, within a fraction of a light year of the event horizon, the gravitational forces are so intense that they can actually distort the stars themselves. A red clump giant on a highly elliptical orbit that sweeps it perilously close to the black hole could experience tidal forces powerful enough to stretch and compress it during its closest approach, a process called tidal straining. While not as dramatic as the complete disruption that happens to smaller stars, this effect could subtly alter its oscillation modes or even strip away some of its outermost atmosphere. Observing such stars offers a unique laboratory for testing general relativity in its most extreme regime. Furthermore, the intense ultraviolet radiation and X-rays pouring from the hot accretion disk around the black hole could potentially erode the outer envelopes of these giants, affecting their apparent color and evolution. Studying how these stars survive or don't in this brutal neighborhood teaches us about the limits of stellar resilience and the feedback processes between supermassive black holes and their stellar environments. They are the canaries in the cosmic coal mine, showing us just how extreme conditions can get before a star's predictable nature is fundamentally challenged. Ultimately, the red clump giants in galactic centers are more than just distance markers. They are the key witnesses to the dynamic and often violent life of a galaxy's core. Their spatial distribution reveals whether the central star cluster formed in a single, rapid collapse or through the gradual infall and dissolution of smaller star clusters over time. Their chemical composition, measured through painstaking spectroscopic analysis, tells us about the metal enrichment history of the very first stars to form in the galaxy, as the center is likely the oldest component. Perhaps most intriguingly, their collective motions can reveal the ghostly imprint of a past cataclysm, the merger of two supermassive black holes. If our galaxy's central black hole merged with another in the distant past, the gravitational shockwaves from that event would have scrambled the orbits of the surrounding stars. By carefully mapping the motions of thousands of red clump giants, astronomers can search for the faint, leftover patterns that hint at such a monumental collision. So, while they may appear as simple, steady points of light in the galaxy's chaotic core, each one is a data point in a grand narrative of birth, chaos, and survival. They illuminate not only the vast distances to these mysterious regions, but also the profound physical processes that govern the most energetic engines in the universe, proving that even in the face of a supermassive black hole, the consistent glow of a retired star can be a powerful source of cosmic truth. This consistent glow and predictable motion of red clump giants grants them a role far beyond simple distance markers. They become our most effective tracers for mapping the invisible, the cosmic ghost that we know as dark matter. We've learned that the gravity of visible matter stars, gas, and dust is not nearly enough to hold galaxies together or to explain the motions we observe. Something else, something that does not emit, absorb, or reflect light, must be providing the extra gravitational glue. This dark matter makes up about 85% of the universe's total mass, yet it remains utterly mysterious. We cannot see it directly, so how do we possibly map its distribution? The answer lies in using what we can see as a probe for what we cannot, and red clump giants with their well-measured distances and velocities are perfect for this cosmic detective work. It's like trying to map the shape of a valley on a foggy night by watching the paths of drifting hot air balloons. You can't see the valley itself, but by carefully tracking the speed and direction of the balloons as they are pushed by the wind flowing down the slopes, you can reconstruct the entire hidden landscape beneath them. Red Clump Giants are our celestial hot air balloons, and their motions are dictated by the gravitational slopes of the dark matter valley they move through. The most powerful application of this is in the Milky Way's halo, that vast spherical cloud of ancient stars and globular clusters that surrounds our galaxy's main disk. This region is dominated by dark matter. There is very little visible stuff out there to create significant gravity. Yet, when we measure the velocities of stars in the halo, we find they are moving incredibly fast, much faster than the pull from the visible mass of the galaxy could possibly allow. These stars should have flown off into intergalactic space long ago unless they are being held in the grip of an immense, unseen mass. To measure this precisely, you need a star whose true distance and true velocity you know with confidence. This is the perfect job for a red clump giant. Its reliable brightness gives us a precise distance, and its spectrum allows us to measure its line of sight velocity, how fast it is moving towards or away from us. Combine this with its motion across the sky from missions like Gaia, and you get its full three-dimensional velocity vector. When you do this for thousands of halo red clump giants, you can start to build a picture of the gravitational field they are responding to. Stars on circular orbits at a certain distance from the galactic center must be feeling a specific amount of gravitational pull to maintain that orbit. If their measured speed is higher than what the visible mass can account for, the difference must be due to dark matter. By repeating this calculation at different distances throughout the halo, we can essentially weigh the Milky Way and plot out how much dark matter is present at various radii, constructing a mass profile for our galaxy's invisible skeleton. This technique has led to one of the most important diagrams in modern galactic astronomy, the galactic rotation curve. This is a graph that plots the orbital speed of stars and gas against their distance from the galactic center. Based on the visible matter alone, we would expect that beyond the bright central bulge, the rotation speed should fall off, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. But for the Milky Way and every other spiral galaxy we've studied, the rotation curve remains flat far out into the halo. The stars and gas at the visible edge of the galaxy are orbiting just as fast as those closer in. This was the first and most compelling evidence for dark matter, and red clump giants in the outer halo provide the crucial data points that extend this flat curve to its greatest distances. They show unequivocally that the unseen mass is not concentrated in the center, but is spread throughout a massive, diffuse dark matter halo that extends far beyond the last visible star. Their precise distances are what make this measurement so robust, anchoring each velocity day to point to a specific location in the galactic gravitational well. But the story gets even more fascinating when we look at the collective motion of these halo giants, not just their individual speeds. Dark matter is not thought to be distributed in a perfectly smooth and uniform sphere. Our leading cosmological model, which includes cold dark matter, predicts that the halo should be lumpy, filled with substructure like streams, clumps, and even smaller, dark subhalos that never manage to form many stars. Finding this substructure is a major goal, and it's like trying to find islands in a dark ocean by watching the behavior of ships. If you see a large group of ships all suddenly changing course or accelerating in unison, it suggests the presence of a hidden landmass affecting the currents. In the galactic halo, these ships are streams of stars, often the remnants of devoured dwarf galaxies. Red clump giants are ideal for identifying these streams. Because we can measure their distances and motions so well, we can find groups of them that are not just near each other, but are moving together on the same path through space. When we map these stellar streams, their very shape is a sensitive probe of the dark matter distribution. A smooth, symmetric dark matter halo would produce streams that are long and relatively straight. But if a stream shows kinks, gaps, or sharp density changes, It's a strong indicator that it has recently passed through a clump of dark matter whose gravity perturbed the star's orbits. By studying these perturbations in streams traced by red clump giants, astronomers can indirectly detect the presence of otherwise invisible dark matter subhalos, testing a key prediction of our fundamental model of the universe. This entire endeavor is pushing toward an even more profound goal, determining the density and shape of the dark matter halo closest to home. Is the Milky Way's dark matter halo perfectly spherical, or is it flattened like a squashed ball? The answer has implications for the fundamental properties of dark matter particles themselves. By using the three-dimensional velocities of red clump giants at different galactic latitudes, some close to the disk plane, others high above it, scientists can measure the forces acting in different directions. This allows them to reconstruct the overall gravitational potential, which reveals the shape of the mass distribution causing it. Current evidence, heavily reliant on precise tracers like red clump giants, suggests our dark matter halo is mildly flattened, more like a rugby ball than a beach ball. This simple geometric fact helps rule out certain theoretical models for what dark matter could be, guiding physicists in their search for this elusive substance in underground laboratories and particle colliders. So, the steady, predictable light of a red clump giant in the lonely galactic halo does more than just tell us how far away it is. It acts as a single pixel in a grand, invisible map. By combining millions of these pixels, we slowly bring into focus the hidden architecture of our universe. An architecture built not of stars and gas, but of a mysterious substance that governs the very fate of galaxies. You might think that this kind of cosmic cartography is reserved for professional astronomers with access to giant telescopes and supercomputers, but one of the most exciting developments in modern astronomy is how it's opening its doors to everyone. All of those massive sky surveys we talked about, missions like Gaia, Kepler, and the upcoming Vera-C, Rubin Observatory, don't just produce pretty pictures, they generate almost unimaginable amounts of raw data. We're talking about billions of stars, each with measurements of its brightness, color, and position. For a small team of professional researchers, sifting through this avalanche of data to find and classify all the red clump giants is like trying to count every grain of sand on a beach by yourself. This is where the power of the crowd comes in, through a vibrant global movement known as citizen science. These projects harness the pattern recognition skills of thousands of volunteer observers from all over the world, turning anyone with a curiosity about the universe into an active contributor to the frontiers of knowledge. It's a beautiful partnership. The professional astronomers build the instruments and collect the data, and a distributed global network of dedicated amateurs helps make sense of it all. You don't need a PhD in astrophysics to participate. All you need is a willingness to learn, a keen eye, and an internet connection. This collaborative spirit is revolutionizing fields from planetary science to galaxy classification, and the hunt for red clump giants is a perfect example of how your living room can become a portal to the cosmos. One of the most prominent platforms for this work is the Zooniverse website, a collection of online citizen science projects that have engaged millions of volunteers. A project specifically focused on stars might present you with a simple, user-friendly interface. On one side, you'd see a color magnitude diagram, that fundamental family tree of stars we discussed earlier, plotted with thousands of data points from a particular star cluster or a patch of the Milky Way. On the other side, you'd be given a brief tutorial on what to look for. You'd learn that the red clump appears as a distinct, dense knot of points in a specific region of the graph, separate from the long band of the main sequence and the more scattered stars of the red giant branch. Your task would be to look at the diagram and click on that cluster. It might sound simple, but the human brain is exceptionally good at this kind of visual pattern recognition, often outparenting even sophisticated computer algorithms, which can sometimes be confused by background noise, unusual stellar populations, or subtle effects from dust. By having thousands of people look at the same data, the project builds a consensus. If hundreds of volunteers independently identify the same tight grouping of stars as the Red Clump, the professionals can be highly confident that's what it is. Your clicks are collectively building a reliable, human-verified catalog of these standard candles across the galaxy. Each classification you make is a small but genuine act of scientific discovery, adding another data point to our three-dimensional map of the Milky Way. The contributions of citizen scientists in this area have led to tangible, published scientific discoveries. Volunteers have helped identify red clump giants in nearby dwarf galaxies, pinning down their distances with greater accuracy and providing new insights into the structure of our local group. They've also been instrumental in finding rare and interesting outliers. For instance, by scanning through vast datasets, amateurs have occasionally spotted red clump giants that appear to be much brighter or fainter than the norm. These aren't errors, they are clues. An anomalously bright red clump giant might actually be a binary star system where two red clump giants are orbiting each other, their combined light making them stand out. A faint one might be a star that has an unusual chemical composition, or it could be located behind an unexpected patch of dust that dims its light. When volunteers flag these peculiar objects, they bring them to the attention of professional astronomers who can then follow up with detailed spectroscopic observations using large telescopes. This process of weird object discovery is a fantastic example of the symbiotic relationship between humans and machines in the big data era. The algorithms can efficiently process the mundane, but the curious human eye is brilliant at spotting the unusual, the thing that doesn't quite fit, which is often where the most exciting new science is hiding. But what does this process actually feel like from the volunteer's perspective? Imagine sitting down at your computer in the evening, perhaps with a cup of tea, and diving into data from the European Space Agency's Gaia mission. You're not just looking at abstract numbers, you're presented with a beautiful, intricate scatter plot, a map of a specific stellar family. As you complete the tutorial, you learn to recognize the characteristic shapes. You see the main sequence sweeping diagonally across the plot, and then, just where the tutorial said it would be, you spot it, a beautiful, tight clump of stars, a little island of consistency in a sea of stellar diversity. There's a genuine aha moment when you successfully identify your first red clump. You realize that you are not just playing a game, you are looking at the real, observed properties of real stars thousands of light years away. With each click, you are helping to place another beacon on the cosmic map. Many projects also include online forums where volunteers can discuss tricky cases, ask questions of the research team, and share their excitement over interesting finds. This creates a real sense of community, connecting people from different backgrounds and countries through a shared passion for unraveling the mysteries of the galaxy. It's a powerful reminder that science is not a remote, ivory tower endeavor, but a collaborative human adventure, and that the desire to explore and understand the universe is a universal trait that we can all participate in. The impact of this public participation extends far beyond just creating a larger catalog. By involving a global community, citizen science projects are also fulfilling a vital educational and inspirational role. They demystify the scientific process, showing people firsthand how classification, statistical analysis, and collaborative verification actually work. A student who spends an hour classifying stars on Zooniverse gains a much deeper and more intuitive understanding of the Hertzsprung-Russell diagram and stellar evolution than they could from any textbook. They are learning by doing. Furthermore, this open model of research fosters a greater sense of public ownership and trust in science. When people contribute directly to a project, they develop a personal stake in its outcomes. They follow the research papers that get published, feeling a pride of ownership knowing that they played a part in that discovery. This helps bridge the gap between the scientific community and the public, creating a more scientifically literate and engaged society. In the specific case of Red Clump Giants, every volunteer who helps identify them is strengthening the very first rung of the cosmic distance ladder. They are contributing to the foundational data that will be used to measure the Hubble Constant with greater precision and perhaps to ultimately resolve the Hubble tension. So the next time you look up at the night sky, remember that you don't need $1 million telescope to be an explorer. The data is out there waiting for your eyes. With a simple click, you can join the hunt for these celestial lighthouses and help us all chart the vast, beautiful, and still mysterious cosmos we call home. But what does this entire process of discovery, from theory to mapping, actually look like on the ground? Let's pull back the curtain and follow a hypothetical astronomer, Dr. Lena Vance, through a typical day in her quest to understand the cosmos using these stellar mile markers. Her day doesn't always begin under the stars. It often starts in a brightly lit office, the quiet hum of computers serving as the soundtrack to her research. The first task might be to review the most recent data release from the Gaia Space Observatory. Think of this as checking a cosmic stock ticker that has just updated with millions of new entries. She isn't just looking at numbers, she's using specialized software to visualize a specific star cluster in the galactic halo, plotting a color magnitude diagram. Her trained eye immediately scans for that telltale tight grouping, the red clump. With a few clicks, she can select all the stars in that clump, and with Gaia's incredibly precise parallax measurements, the software instantly calculates their distances. In a matter of minutes, she has confirmed the cluster's location in three-dimensional space, a task that would have taken years of painstaking observation just a generation ago. This is the power of modern survey astronomy. It's like having a universal catalog of stellar properties updated in near real time, allowing her to test hypotheses and make discoveries at a breathtaking pace. As the morning progresses, her focus might shift from broad surveys to a specific, puzzling target. Perhaps she's studying a stream of stars in the Milky Way's halo, the remnants of a devoured dwarf galaxy. The Gaia data shows the stream, but to confirm it's a single, coherent structure and not a chance alignment, she needs more than just positions and distances. She needs velocities. This is where her precious, scheduled time on a large ground-based telescope comes into play. A few nights each semester, she'll connect remotely to an observatory in Chile or Hawaii. She won't be physically looking through an eyepiece. Instead, she'll be controlling the telescope and its powerful spectrograph from her office. Her target list for the night will be populated with candidate red clump giants along the stellar stream. One by one, the telescope will slew to each star, its light gathered by the massive mirror and funneled into the spectrograph. This instrument doesn't just capture a pretty picture, it acts as a cosmic prism, splitting the star's light into a rainbow. Superimposed on that rainbow are dark lines, the unique fingerprints of the elements in the star's atmosphere. The precise position of these lines holds the key. A subtle shift toward the red end of the spectrum reveals the star's velocity away from us. As the data trickles in, she watches the velocities of the stars in the stream. If they all share a similar, distinct motion compared to the background halo stars, it's a eureka moment. She's not just seeing a group of stars, she's witnessing the ghost of an ancient galaxy. Its stellar population still moving in unison billions of years after its destruction. This combination of Gaia's mapping and targeted spectroscopic follow-up is how the invisible architecture of our galaxy is slowly, painstakingly being revealed. After a night of data collection, the next day is dedicated to making sense of it all. This is where the real detective work begins, often involving complex computer simulations. Let's say Lena has a catalog of red clump giants from a nearby galaxy, courtesy of the Hubble or James Webb Space Telescope. Her goal is to measure the galaxy's distance. The raw data is a list of stars and their apparent brightness. Her first challenge is to correct for interstellar dust, which dims and reddens the starlight. She'll run sophisticated algorithms that model the dust distribution, using the star's colors across multiple wavelengths to calculate a correction factor for each one. Once the data is cleaned, she'll plot the final color magnitude diagram. There it is, the beautiful, distinct clump of red clump giants. Now, using their known calibrated true brightness, she compares it to their corrected apparent brightness. The difference is direct and mathematical, yielding a precise distance to the galaxy, but her work doesn't stop there. Perhaps she notices that the clump is slightly broader or brighter than expected. This could be a clue. Is it due to a range of metallicities in the stellar population? Or could it be that some of the stars are actually unresolved binaries, two red clump giants orbiting each other, making them appear brighter? To test these ideas, she'll turn to stellar evolution models. She'll run computer simulations that take a virtual population of stars with a range of masses and metallicities and let them evolve over billions of years. The model will predict where these stars should land on the color magnitude diagram. By tweaking the initial conditions, the star formation history, the chemical composition, she can try to make her simulated diagram match the one she observed. It's a process of iteration and refinement, a dialogue between theory and observation that slowly unravels the complex history of the galaxy she's studying. This cycle of observation, analysis, and simulation is the heartbeat of modern astronomy. It's a profession that demands patience, as a single research project can span years, and a single night of telescope time can be lost to a passing cloud. But it's also a field filled with moments of profound wonder. For Lena, that wonder isn't just in the spectacular images, it's in the clean elegance of a data plot that confirms a prediction, or in the quiet satisfaction of finally getting a stubborn computer model to match the real universe. It's the realization that she is using the predictable, steady light from a population of aging stars, millions of light years away, to answer fundamental questions about the cosmos. Her work, and the work of thousands of astronomers like her, transforms the abstract beauty of the night sky into a precise and measurable reality, one red clump giant at a time. Beyond their profound scientific utility, there is a raw, visual poetry to these stars that captivates the imagination. Picture a red clump giant not as a mere date, a point on a graph, but as a celestial ember glowing with a deep, resplendent crimson. This is not the brilliant white of a young, frantic star, nor the pale yellow of a middle-aged sun like our own. This is the rich, warm hue of stellar maturity, the color of a cosmic bonfire that has been burning steadily for tens of millions of years. In artists' impressions, which translate the dry data of temperature and luminosity into visual grandeur, these stars are often depicted as colossal orbs of fiery orange and deep red, dominating their corner of space. They are the rubies of the galaxy, their light a testament to a long and eventful life. To understand why they glow with this specific color, we need to think about a campfire. The hottest, most energetic part of the flame, right at the heart, burns a brilliant blue-white. But as you move to the outer edges where the temperature is cooler, the glow shifts to a deep, comforting orange and red. A red clump giant is like the outer embers of that cosmic fire. Its surface temperature is much cooler than it was in its youth, typically around 4,000 to 5,000 degrees Celsius compared to the Sun's 5,500. This lower temperature means it radiates most of its light in the red and infrared part of the spectrum, gifting it that distinctive, warm complexion. It's a star that has expanded and cooled, trading the intense blue-white vigor of its prime for a larger, more serene, and visually striking crimson radiance. Their place in the cosmic landscape is one of quiet dominance. Imagine a wide-field telescope image of a distant, face-on spiral galaxy. Your eye is first drawn to the brilliant blue knots in the spiral arms, where fierce, young, massive stars are being born. These are the stellar nurseries, dazzling and energetic, but then you notice the galaxy's central bulge, a soft, glowing yellowish orb, and within that glow and scattered throughout the galactic disk are the countless points of light from red clump giants. They don't scream for attention like their blue siblings. They provide a steady, foundational light. They are the background illumination, the mature population that outlines the galaxy's permanent structure, long after the flashy blue stars have burned out in spectacular supernova. In a dense globular cluster, a spherical swarm of millions of ancient stars, the color magnitude diagram reveals a stunning fact. A huge fraction of the brightest stars you can see are, in fact, red clump giants. Their combination of intrinsic brightness and longevity means that in these old communities they rise to the top, becoming the most prominent citizens. Looking at an image of a globular cluster like Omega Centauri, what appears as a dense, shimmering cloud of stars is in many ways a congregation of these red and orange giants, their collective light defining the cluster's warm, golden hue. They are the elder statesmen of the stellar population, their consistent glow providing both the light to see the cosmos and the markers to measure it, connecting the grand architecture of galaxies to the intimate life cycle of a single star. This connection between their physical nature and their aesthetic impact is what transforms them from abstract concepts into objects of genuine awe. When you learn that the deep red color is a direct result of the star's expansive, cool outer layers, you are seeing the physics of stellar evolution made visible. That gorgeous hue is a symptom of the star's advanced age and its internal stability. The very process that makes it a reliable standard candle, the steady helium fusion in a degenerate core, is what gives it its majestic appearance. There is a profound beauty in that synergy, where scientific utility and visual splendor are born from the same underlying physical reality. It's a reminder that the universe is not just a collection of cold, mechanical processes, but a place of immense and often breathtaking artistry. The laws of physics, when played out on a cosmic scale, produce objects of stunning elegance and power. The red clump giant is a perfect embodiment of this principle. Its predictable luminosity makes it a tool for science, but its serene, crimson glow makes it a masterpiece of nature. To truly appreciate one is to appreciate the other. The awe we feel when gazing upon an impression of this stellar retiree is the very same awe that drives us to understand its inner workings. It represents a moment of cosmic balance, a temporary but long-lasting peace in the otherwise turbulent life of a star, and in doing so, it offers us a point of connection to the vast, dynamic, and beautiful universe we are so privileged to explore. One of the most persistent misunderstandings about cosmic standard candles is the idea that they are all perfect clones of one another, each an identical cosmic light bulb rolling off a universal assembly line. This notion of flawless uniformity is appealing in its simplicity, but it doesn't reflect the beautiful, nuanced reality of stellar physics. The truth is, when we call a group of stars standard candles, we are describing a population with a remarkably tight distribution of brightness, not a single fixed value. Think of it like a factory producing 100-watt bulbs. While the design calls for 100 watts of output, the actual bulbs might vary slightly. Perhaps a few shine at 98 watts, while others glow at 102. The key is that this variation is small, predictable, and most importantly, measurable. For red clump giants, this means their intrinsic luminosity clusters incredibly tightly around a value about 50 times brighter than our Sun, with a typical spread of only about 5 to 10%. This small range is what makes them so useful, not a non-existent perfection. Astronomers don't just assume a single number, they work with this entire distribution, using statistical methods to account for the natural spread. This allows them to achieve high precision even with a population that has slight, natural variations in properties like initial mass or chemical composition. The power comes from the collective, from analyzing dozens or hundreds of these stars in a single galaxy, where the random variations average out to reveal a rock-solid, reliable mean brightness. So they are not perfect identical twins, but more like a large family of siblings who all share a strong, recognizable family resemblance in their luminosity, a consistency that is more than enough for the precise work of cosmic cartography. Another widespread misconception is that once you've identified a standard candle, calculating its distance is a simple, one-step mathematical division. The impression is that you just plug two numbers into a formula and get an instant answer. The reality is far more complex and involves a rigorous process of cosmic forensics. The biggest complication is interstellar extinction, the dimming and reddening of starlight caused by vast clouds of cosmic dust that drift between the stars. This dust doesn't just make a star look fainter, it also makes it look redder, mimicking the natural color of a cooler star. If an astronomer were to simply measure how faint a red clump giant appears and immediately attribute all of that dimming to distance, they would be making a catastrophic error, potentially overestimating the distance by a significant margin. Correcting for this effect is a multi-step, painstaking process. Astronomers must observe the star through multiple filters, measuring its brightness in different colors from blue to infrared. The specific way the star's light is dimmed and reddened across this spectrum acts as a fingerprint for the amount and type of dust in the line of sight. Only after this detailed dust map has been created and applied can the true, undimmed apparent brightness of the star be revealed. Then, and only then, can it be compared to its known intrinsic brightness to yield an accurate distance. It's a far cry from a simple calculation. It's a careful, iterative cleaning of the data, ensuring that what we're measuring is truly the effect of vast distance and not just a local cosmic haze. Perhaps one of the most crucial distinctions for the public to grasp is the difference between a red clump giant and the more general category of red giant branch stars. From a casual glance, they can look quite similar. Both are large, cool, and red. But their internal lives and their value as distance markers could not be more different. A red giant branch star is in an earlier, more chaotic phase of life. It has exhausted the hydrogen fuel in its core and is now burning hydrogen in a shell around an inert helium core. This is a transient and unstable period. The star is rapidly changing, its brightness and size in a state of flux as it searches for a new equilibrium. Because stars of different initial masses pass through this phase at different rates and luminosities, red giant branch stars are scattered across a wide range of brightnesses. They are a diverse population, not a standardized one. The red clump giant, in stark contrast, represents a period of calm retirement after the storm. It has successfully ignited helium in its core and entered a long, stable phase of helium fusion. This core helium burning phase acts as a great cosmic equalizer, forcing stars of a range of initial masses into a very narrow range of luminosity and temperature. This is why they appear as a distinct tight clump on the Hertzsprung-Russell diagram, while the red giant branch stars form a broad ascending band. Confusing the two would be like mistaking a group of teenagers all growing at different rates and heights for a group of fully grown adults who have all reached their stable, mature stature. Using a red giant branch star as a standard candle would introduce enormous errors, as its brightness is a moving target. The ability to cleanly separate these two populations using color, surface gravity measurements, and their distinct positions on the color magnitude diagram is therefore a foundational skill in modern astronomy, one that ensures the integrity of our cosmic distance scale. A more subtle but equally important misunderstanding revolves around the belief that standard candles provide a single, definitive answer. In reality, every published distance to a galaxy using red clump giants comes with an attached uncertainty, often expressed as plus or minus a certain number of light years or a percentage. This uncertainty isn't a sign of failure, it's a hallmark of rigorous science. It represents the careful accounting of all the potential error sources, the natural spread in the star's luminosities, the residual uncertainty in the dust correction, the challenge of crowding in dense stellar fields, and the difficulty in perfectly separating true clump stars from imposters. Modern papers don't claim a single, absolute distance. Instead, they present a probability distribution. They might state that the distance to the Triangulum galaxy is most likely 2.77 million light-years, with a 68% confidence that the true value lies between 2.72 and 2.82 million light-years. This statistical approach acknowledges the complexities of the measurement while still providing a result of immense value. Furthermore, astronomers never rely on a single method if they can help it. The distance to a key galaxy like Andromeda is cross-checked using multiple techniques: Red Clump Giants, Cepheid variables, eclipsing binaries, and even the tip of the red giant branch, which is a different but also standardized feature. When these independent methods, each with their own strengths and weaknesses, all converge on a similar answer, our confidence in that distance soars. This multi-pronged statistical approach is the true backbone of the cosmic distance ladder, a far more robust and honest system than the simplistic idea of reading a single number from a single, perfect star. So, after this incredible journey, what are we left with? We started with a simple yet profound question. How do we measure the universe? And we discovered that the answer lies not in a complex machine or an abstract equation, but in the predictable, steady glow of a specific kind of aging star. The Red Clump Giant, a star in its comfortable retirement phase, has become one of the most trusted tools in the astronomer's kit. Its story is a beautiful synthesis of stellar physics and cosmic exploration. We learned that its reliability comes from a universal rite of passage for sun-like stars, the ignition of helium in a degenerate core, a process that acts as a great cosmic equalizer, forcing a vast population of stars into shining with nearly identical brightness. This isn't a small convenience, it's the foundation upon which we build our map of the local universe. These stars are the crucial middle rung on the cosmic distance ladder, the indispensable bridge between the geometric measurements within our own galaxy and the vast, expanding cosmos beyond. They provide the stable anchor that allows us to calibrate brighter, more distant beacons, ultimately letting us measure the expansion rate of the universe itself. Without them, our cosmic address would be a guess, the structure of our own Milky Way a mystery, and the grand narrative of an expanding universe would be built on shaky ground. They transform the night sky from a beautiful, two-dimensional tapestry into a measurable, three-dimensional reality, giving depth and scale to the cosmos. Think about the sheer scope of what these stars illuminate. Within our own Milky Way, they have acted as our master surveyors. Their consistent light has pierced through the obscuring dust of the galactic plane, allowing us to trace the elegant spiral arms we call home. They revealed the boxy, peanut-shaped bulge at our galaxy's heart, a dynamic structure shaped by billions of years of gravitational interaction. They helped us map the subtle warp and flare of the galactic disk and trace the ghostly stellar streams in the halo, the remnants of ancient galaxies consumed by our own in the deep past. This isn't just mapping, it's galactic archaeology, and red clump giants are the primary fossils we use to piece together the biography of our galaxy. When we look beyond our own borders to the Andromeda and Triangulum galaxies, these same stars become our intergalactic ambassadors. Their identifiable glow in those foreign stellar populations gives us a direct, precise measurement of their distance, transforming them from fuzzy smudges in a telescope into known islands in the cosmic ocean, with defined places in the architecture of our local group. This local mapping is the essential first step in a chain that stretches to the edge of the observable universe, a chain that tests our most fundamental theories of physics. This brings us to the ultimate implication of this work, the Hubble tension. The fact that the humble, local red clump giant finds itself at the center of one of cosmology's biggest modern mysteries is a testament to its fundamental importance. The precise distances we get from these stars anchor one end of the cosmic distance ladder, leading to a measurement of the universe's current expansion rate that stubbornly disagrees with the prediction from the early universe. The reliability of the Red Clump Giant data gives us confidence that this discrepancy is not a simple error but a potential clue. It suggests that there might be something missing from our standard model of cosmology, a new property of dark energy, a new type of particle, or a fundamental misunderstanding of how gravity works on the largest scales. The quiet, consistent burning of these stellar retirees is therefore challenging our understanding of reality itself, proving that the most local cosmic phenomena are inextricably linked to the grandest questions about the nature of the universe. It's a profound thought that the predictable end of a star's life provides the light by which we understand the beginning and fate of everything. From a single, stable star, we have built a tool that illuminates the structure of galaxies, the history of cosmic assembly, and the dynamics of the expanding universe. This journey from stellar retirement home to fundamental cosmic probe showcases the beautiful interconnectedness of the cosmos, where the laws of physics governing a single star also govern the entirety of existence. The next time you find yourself under a clear, dark sky, take a moment to truly look up. Let your gaze wander from the bright, familiar constellations to the fainter, milky band of the Milky Way. And as you do, remember this: scattered across that vast expanse, from the nearby star clusters to the hearts of distant galaxies, are countless crimson beacons, the Red Clump Giants. They are out there right now, burning steadily, silently providing the measurements that allow us to comprehend the breathtaking scale of it all. You are not just looking at pretty lights, you are looking at a map, a history book, and a laboratory for fundamental physics, all written in the light of these celestial lighthouses. So go outside, look up, and ponder the immense distances to the stars. The cosmos is not an impenetrable mystery. It is a story we are learning to read, one predictable, glowing giant.